So today I'm going to discuss about sources of medical images. So I'll tell you about the data set, online data set, which is available especially for medical images. Okay, so we'll move with it. Voice breaker. Voice breaker. No. So let me start with medical image processing. Am I clear whether my voice is clear or not? Please respond anyone. So I'll start so that
Yes,
we'll
ma'am, it
start
is
with
clear.
yeah, thank you. Okay, so I'll start with medical image processing. So as like that, yesterday, however, we have this, we got such discussions like denoising, enhancing. So the same technique here also we have to start that too, particularly for the medical images. Definitely, image noise is much like speckle noise will be there. Salt and pepper will be there. So it depends on if X-ray in the sense salt and pepper is a common and Gaussian will be the common noises. So in such a way, the medical image in the sense first we have to enhance the image by removal of artifact or we can correct the color. So likewise we have to proceed that. Yeah, first we can enhance the source image. We can remove the artifact. Color correction in color medical images. Nowadays we are having the color medical images like PET images, PET. So PET images are color like images because which helps like blood circulation and all will be captured in that image. Based on the blood circulation, the image will be captured. So that in that also the color correction can be done. And then manipulating the colors. See, for example, in X-ray, it's a grayscale like image. So what we'll do, we can manipulate, we can feed the colors wantedly, that is by doing research in order to identify the abnormality, where the abnormality is, we can manipulate the colors. So that also can be done as an image processing technique. And then segmentation. So abnormality segmentation or anatomy segmentation in medical images we can do. And then generating content detection, obviously outline detection. And then generating 3D from 2D images. This is a vital now recent trend which is going on in medical image processing. So we can convert the 2D images into 3D images. So that which helps to identify, which helps for surgical purposes. And then restoration of images. Okay, if any fault, that is restoration in the sense, for example, if the organs or anything is missed or any problem occurs due to any accident or what, we can able to restore that particular part and we can help for reconstruction. So that is nothing but restoration of images. And then smoothing, zooming, and then point to point measurements. What is the distance, okay, between the abnormality or between the anatomy? So that one also can be detected. So how we can help, okay, how we can help for the medical field in the sense, we can develop application oriented systems, okay, for diagnosis purposes. And then charts to maintain the medical records. This and all we can do. And then robotic systems, early detection tools we can create. And then sensor, okay, already they are working with the sensors, right? So we can provide how the blood flow or something like that is good or not. So flow sensors we can do. And then surgical for the surgical tools we can do touch sensors. And then genetic engineering oriented, neural engineering oriented, and the drug oriented research works that we can do. So as we are going for image processing, definitely improving the medical images is very, very important in this field. So here, when we go for X-ray, so X-ray, you all know that there are some data set. So National Institute of Health chest X-ray data set, which nearly contains 5,606 X-ray images. If you are doing any work in X-ray, you can chest X-ray that too particularly. You can prefer this data set. It has the truth values also, so that you can compare that accuracy levels easily by having the truth values. And then other medical images like this is also X-ray and X-ray for bones oriented images. So MURA, okay, musculoskeletal radiographs which is a large data set for this X-ray. Okay, bone oriented. So you can take this for your research work. And then mammograms, that is breast cancer. So for that, a digital database for screening mammogram. Okay, this is one of the data set. It nearly contains 2620 images with the truth values. So you can get, you can use for your work. So CT scan. About the CT scan, after the X-ray, the CT scan which plays a vital role for surgical and diagnosis purpose also. So here you can see several type of CT scans. First is head oriented CT scan. It takes the slice oriented images. Okay, it will not take the total image. Total body can be taken in a slide oriented. So first is head actually. So they'll change small of diameters, means place width every part of our brain. Then they'll take the image. So this is head, and next is shoulder. This is shoulder. See actually in the last two image you can see the 3D like look. So it says the shoulder. So this is a top view. Okay, each and every inch of top view of the shoulders. So this is one, and this is spine. So this is side view of the spine. This is top view of the spine. Okay, first two are top view actually, and this is a side view. So all the views that we can capture through the CT scan. And then knee. Okay, this is a front view, and this is top view of the knee. This round is nothing but the top view of the knee. And here it's heart oriented image. That is heart oriented CT image. Okay, so this is top view. First three are top view, and this is front view. You can see the heart here. Okay, in the fourth slide, you can see the heart total. So this is front view. The same way abdomen. Okay, so abdomen also, this is top view of each and every slide, and this is total view. You can see several other parts also, liver and everything. So this is the front view, total front view. And this is chest. Okay, so we can see that. So all the single slides which says every slide which says some organ part. Okay, you can see the heart also in this place. It's a top view, so we can't see very clearly, but it's a top view of the heart. So likewise, this is the total portion. So these are the online data sets for CT scan for different organs. Head, we can take from NIH Clinical Center. It nearly consists of 32,000 CT images. Okay. And then shoulder, MDCT data sets, orthography of shoulder. If you type this, same thing, you will get the data set actually. Then spine also, bone CT scan data. This is a website, and then biomedia. So from these two, we can get the spine. The knee, bone CT scan data, we can get it. Actually, in bone CT scan data itself, spine, knee, almost more folders are there actually. You can get it more than that. And then heart, TT MRI data from EX, Bio, canine, and human hearts. This is one website. So you will get the heart that is focused towards the heart-oriented CT scan. And then abdomen, this is one website. Okay, cancer imaging archive. So from that you will get the abdomen related data sets. And chest, NIH Clinical Center. So in that 32,000 CT image. This is a common thing. Everyone knows actually. So NIH Clinical Center, you will have more CT images actually. So head, chest, this is very particular. So with this, shall I stop? So with this, I'll stop. So yeah, yeah. And then for the MRI, let me say I stopped. 1 minute, sorry. Yeah, and for the MRI, head related data sets is there. Bone and joints related separate data sets are there. Breast related data set, and other internal organs like liver and heart. So separate data sets are there, and most of the data sets will be having the truth values also. For your research work, you can utilize those. So this is a sample of MRI scans. Okay, this is for head, and this is for joints. Okay, leg joints and hand joints, and this is for clear abdomen, and this is for breast. Okay, this is from top view actually. Yeah, dental data set, I'll show you. Ultrasound, this is. So dental, as the request comes, I'll show dental oriented. Dental panoramic X-rays. Okay, in this you can find dental oriented datasets. So, okay. Okay. So other than that, yeah. Thanks a lot. Okay. And then also, yeah, thank you. And then ultrasound, shall I stop or?
Hasn't responded. You just see whether you can complete it.
Yes. Let me see. Text பண்ணுங்க. Madam on WhatsApp. Please 1 minute.
I have joined.
Yes, ma'am. Yes. Shall we start, ma'am? Yes, we can. Okay, okay, participants. I'll start now. Thank you all.
I think like based on the request.
Two, session 1. We are starting with day 2, session 1. We have Dr. Shiba Rani, Associate Professor in Indian Institute of Space Science and Technology, Trivandrum. Madam has 23 years of experience in teaching, and her area of research interest includes computer vision, pattern recognition, image analysis, and understanding. She is also an expert in design and performance evaluation of hardware solutions for signal and image processing techniques. She has a couple of funded projects from MIT, and she has also completed funded projects from IIST ISRO. She has 2 patents to her credit and 10 journal publications in peer-reviewed journals. I invite you cordially for this session, ma'am. Now I hand over the dais to you. Kindly proceed, madam. Shivarani, madam, I made you as the presenter. Can you hear me, ma'am?
Yes.
Madam, can you please share your presentation so that I will just check whether you are able to navigate, and then I will completely hand over the session to you.
Yes. Let me check it now.
Yes, ma'am. Please, you just open your screen and you can see a share button down.
Could you see my presentation?
Yes, ma'am. I'm able to see it.
Yes.
Then I'm handing over the session to you, ma'am. You please kindly proceed, madam.
Okay. So here to make the audio video on, initially I can make the video on, right? Okay. Whether my video is available? Could you hear me? What? Hello?
Ma'am, there is a voice break.
Oh.
That's what.
Could you hear now?
Ma'am, once if you can switch on the camera, not
my camera
video,
is on,
ma'am.
but,
Click on start video below.
Yes. Now
there is one start video. Yes, ma'am. Now I'm able to see you.
Okay.
Yeah, 2 minutes, ma'am. I'll just take a snap and then you can.
Okay.
Yes, ma'am. Now you can proceed. You can switch off and you can proceed, ma'am.
Yes. 1 minute. Connecting my friend. Okay. Good morning to you all. So today, in the first session, we are going to see about image segmentation. So in the first day of the FDP, you might have learned or you might have heard about the basics of image processing. So in continuation with that, as we know that
Ma'am,
the
there is a
image,
voice break, ma'am.
okay, but here connectivity is good only, but let me check it.
Excuse me, ma'am.
Yes,
Can you please make this full screen, the presentation mode?
yes. Thank you.
Okay, thank you.
Is it okay now? Is my voice audible now? Is there any problem in connectivity now?
No, ma'am. No, ma'am.
No, yes, thank you.
No, it is
So
fine.
in the past, yes. So in the past previous day, you have learned about or you heard about the image processing. The image processing, we are having two types of processing. One is low level image processing and another one is high level image processing. So low level and high level. So the first class is you might have heard about low level. In low level, the input is image, output is also, we are saying it is image. That means image enhancement, filtering, these tasks, we are calling it as low level image processing. When we are going for the next level, that is high level image processing. In high level image processing, the input is image, but output, it's not necessary that it has to be a image. It can be a part of the image or it can be some features which is used for some other higher level of applications. That means we can say that for image understanding, computer vision problems. So for any type of applications, we'll be going for these types of high level image processing. But for this high level processing, the part of a low level is very much important because we know image enhancement is a very important task which is required to get a very good high level image processing representation, which leads to applications of many applications we can say, right? So image understanding, any type of applications we can see. So in this today's session, the major processing we are going for is, we can say that one sort of high level image processing, which is called the image segmentation. Okay. So what is image segmentation? So the image segmentation, you see an image which is here, which is having some backgrounds and some objects. This segmentation task, it depends upon that how it is subjective in nature. That means for some persons, this background may be important. For some people, this object or the tiger may be important. So it is highly contextual and it is highly subjective in nature. So our aim is that we have to get the image or we have to get the part of the data which has to be used for further processing or further recognition or further understanding to do some other task. So here we are just making some segments of images or partition of images or split images or separation of images, pixels, we can say that, based on our interest, and we are giving some meaningful outputs, okay, or meaningful regions. Now when we are seeing this image, we have here this background and this object. So I can say that if I'm only interested in this object, I'm not interested in this. My aim is that how I can effectively represent this portion. or this region, how I will be representing. Or I can say that how effectively I can differentiate this region with this region. That is my segmentation. So now you see that when it undergoes a segmentation process, we can see what are the different types of segmentation, especially clustering we'll be seeing. So here it has represented 4 regions. One is this background, first one. So I name it as 4. This I'm just 3. This is 3, third region. This is my region of interest. This I'm giving as 1. So this is divided 1. And this is another one area of interest in which. So here I am interested in this contact, this object. But you may be interested in the wetland. Somebody will be interested in the pastures or grazing areas in the forest. Suppose this is a forest area. So somebody will be interested in those areas. So we can say that now we will be having different regions of operations. Okay. So this is one, the way in which we will be segmenting. We are having some mathematical operations for segmenting this images, right? So in terms of the mathematical context, we can say that the images can be of having different structures, different shapes. First, what I have told is the regions. Next, it has, we can define that when we are going to one more level down, because everything is done by a computing device, right? So we have to give a meaningful representation so that this region can be effectively segmented. So how we can make it one more level down? We can say that it can be represented by shapes. Shapes can be of anything, circles, ellipses, octagon, pentagon, any shape. How we can define. So mathematically, we can just give some definitions and some procedures we can go for. Then from we can say we'll be having some other structures. That means after shapes, each shape will be having some linear structure. Could you please mute your mic? So that Ahmad, that
टाइम जाया करती हूँ मैं क्या करता हूँ एक ही पेपर में 3 या 4 जगह पे एक रिजेक्ट हो गया दूसरा एक्सेप्ट हो गया इसमें क्या है टाइम की बर्बाद नहीं एक पे ही
Pankaj sir,
जर्नल वाली जो हरामी लोग एक पे ही डिपेंड है पहला भी नोटिस नहीं 2-3 मल्टीपल
excuse me,
हालांकि
Shaukat
इसमें
Ahmad
नहीं
sir,
हुआ
are
दूसरे में
you
होगा
there?
सॉरी
You can continue.
yes. So now when we are
Please
going
mute
for
yourself.
yes shapes. So after shapes, we can go, it is a plane, then we can go one more level down and we can represent that using lines and curves, right? So what we are seeing is that we have to segment the image. Effectively, we have to represent the features using these types of representation to segment, right? So there are different types of segmentation algorithms we can use to segment it. So when we are going for segmentation, there are different types of segmentation algorithms we are having. One is we can go for edge deduction. Since my topic is on clustering, I have not made a presentation for the normal image segmentation. That's why I'm writing here, right? So we can go ahead with clearly the clustering procedures or clustering techniques. So before that, anyway, we should know what are the different types of segmentation which is available. Okay, so we can say that we are having techniques, that is edge deduction techniques. I go fast a little bit. So edge deduction is there. So that's why we can represent any lines or curves or structures can be represented by edge deductors. We are also having shapes using features. We can also represent this. Then the shapes can be represented or can be obtained by region growing algorithms we are having. Another type of segmentation is using histograms, that is thresholding method. This is the common method in which most of the time we are easily following thresholding, right? So thresholding, there are different types of thresholding algorithms in the literature. So now you see that if I'm having edges, if I want to have some edges, edge techniques, if I'm applying, edge means what? Gradient, change of information, right? That is called gradient. So this gradient information, if I'm having from this portion to this portion, there is a change in the pixel intensities or like that. So we will be having a point will be deducted in this region, like that in each and every this like that, an edge is deducted, right? Here it will be having an edge which is deducted because from this region to this region there is a change. So we can say that an edge is deducted. The edge can be a curve, it can be a line. Yes. Okay, so this is thresholding means now you see that I'm having a now you see that this is an image. If I'm taking a 3x3 image, right? I'm having a 3x3 image, 3x3, which is having some 0 to 255 levels, 8-bit representation. So I can say that this region and this region, this color is intensity is high as compared to that of this, or this intensity is high as compared to that of this. If this image I am representing by a 3x3, this color, if I'm having it is very low, if I'm saying it is 10, right? This color, the nearby color, if I'm saying it is 100, 100, here it is somewhat less intensity. So anyway, it is greater than 10, 20, I can say here it is 20. And here I am saying that it is some 15, 15, 15. So this is a 3x3 image. Then I can select a hard thresholding here. Thresholding if the intensity or the pixel, this is an image I, this image is I, right? So I of this, if this threshold is less than 10 or greater than 10, so if it is greater than 10, I am just remaking my pixels. I am just remaking my pixels like this. If it is greater than 10, make it as 1, 1, 1, 1, 1, 1, 1, 1. If it is less than 10, make it as 0. So now you will be getting a binary image which has only two regions. One is this 0 represents the tiger portion and the other region represents this portion. So this is, we are calling it as thresholding. Okay. So just I have given some bare or rough idea about what is this different types of segmentations algorithms we are having. So moving on to that, the other important algorithm in segmentation is clustering. Okay. So normally natural view of segmentation. Okay, quickly. Okay. So normally one natural view of segmentation is that we normally attempt to determine which components of a data set belongs together, right? So now previous diagram, if I am showing, so it will be okay. So if I'm showing the previous image, you just to see that which are the sets or which are the pixels we can group it together, and after grouping it together, how many clusters are there? Based on that, we can segment. So there is a problem in image segmentation known as clustering, right, which is used widely in the literature for image segmentation. So we are having, now I will show you that the problem I have defined is a clustering problem. How we have clustered? That means we are having 4 groups. The similar regions are put together and the dissimilar regions are taken away and it is named as at another groups. So clustering is one natural way or view or in which normally human eye can segment. So in the image processing context, how human beings are segmenting easily in terms of by grouping it or by perceiving it, how we can mathematically make these types of perception into an algorithm to get the segmented output. Okay, so this is also an adopted slide. I have given the source from the data analytics slides I have taken for your understanding. So here image segmentation, one of the broad group is clustering. So in clustering, clustering can be made in two ways in general: partitioning and grouping. So clustering, two major methods we are having in clustering, that is partitioning. Another one is grouping. Okay, so when we are just going for today, we are mostly concentrating on this partitioning method. So when partitioning methods, so under that we are having the famous C-means or K-means algorithm, fuzzy C-means algorithm. All these will be coming under the partitioning. Okay, then we are having hierarchical methods. In hierarchical methods, step by step, will be from the larger group we'll be making smaller groups, or from the smaller groups we'll be making larger groups. That's why we are having two methods. One is the divisive and another one is the agglomerative method. Here we can say hierarchical methods are divisive in nature. Another one we are saying it is agglomerative methods in nature. So when we are just going for agglomerative methods, as from the name itself, we can say that what is this agglomerative means? From the larger groups, right? We will be making a cluster, higher cluster groups. We are making a single cluster. From that single cluster, we are just making smaller clusters. So we can say that we'll be having these methods are somewhat tedious when we are going for this computation, all those things. That also we will see. Okay. Then density-based methods, probability density functions, and distribution methods we are having. That is probabilistic methods we can have, density-based methods. Then graph-based methods are there. Using graphs, we'll be representing the images or data using graphs. And from this, using graph theory, we'll be just segmenting the pixels, grouping the pixels, and we are having algorithms for grouping. Next, we are having it is model-based clustering. In that, it is maybe unsupervised clustering method. So clustering can also be classified into two types, we can say. As part of this, as based on the techniques, we can say it is partitioning and grouping. This is the method. It is done both either in supervised or in unsupervised. Okay, so clustering can be broadly classified as supervised and unsupervised. If it is supervised or unsupervised, what are the techniques which is followed as either partitioning or grouping? So in this grouping methods, we are having hierarchical methods also. That means we are saying that we will be having divisive algorithms and agglomerative algorithms. Right? So we can say that now we can go into the next thing. These algorithms just it is represented. I take slides from here. That's why. Latest also now many algorithms have. These are primitive algorithms. Still we are using these algorithms for this. Okay. 1 minute. Okay, sorry. So we can go ahead with the methods. Okay. Oh, it is not coming. Okay. So
Ma'am,
whatever I
it's fine
told,
now. It is fine now.
okay. Unsupervised clustering, whatever I have told, it is there already, right? So I don't want to explain now. So here in supervised clustering, we can have k nearest neighbors, SVM. So in unsupervised, this is a famous primitive one, hierarchical grouping based on normal correlation, grouping based on weighted that we can see. Okay. So what is k-means? I have just given two definitions for k-means clustering. We are having some pixels, right? So in clustering, we want to group the particular pixels. So we are just defining that we are assuming that if there is n objects in the particular image, right? So in this n objects, we'll be just making k clusters. Okay. So in n objects, we are just having to partition n objects, or we can say that into k clusters in which each object belongs to the cluster. So in n object means this can be pixels or it can be objects. Okay, here I am saying objects in data will be calling it as points. In image, we'll be calling it as, if it's going for a pixel based clustering, we'll be going for n pixels into k clusters in which each object belongs to the cluster with the nearest cluster center. This word we will be seeing what is cluster center. Okay, or we can say in other words, n distinct objects, right? K means k clusters. We are having groups, we are dividing such that in between the cluster, intra-cluster similarity is high, but the inter-cluster similarity is low. So now from this, to define this similarity, we have to define some mathematical function. So here indirectly we can say that what is the objective function, or what we have to concentrate on is some distance function it has to depend on. First thing. Next is that we have to define the number of clusters. So K, we don't know that about the image, but we have to give the how many number of clusters we required, or it is having, based on that only it does. So the distance function we have to define now, and how we are going to proceed with adding the objects in a particular cluster is the algorithm. So as specify K, the number of clusters we are having. Okay, so to group the clusters, any one of the distance metric. So we can say that L1, L2, cosine similarity. These are things you hope you know that, right? So normally this is we are Manhattan. That means we'll be going for Euclidean distance, right? So L1, L2, cosine similarity. These are some of the distance metric that in the literature we are having. So which one, based on that, we'll be selecting that distance metric, and we have to go ahead. So what is this algorithm says is that select k objects at random from a set of n objects, and these k points, that means it's here it is points, instead of that it is objects. K objects are considered as cluster centers. So we can see one tutorial also, then you can able to understand. So in some books we can say it is centroids. The other name for centroids, mathematics, you know, center of gravities. So now how many center of gravities we are having? K center of gravities. Okay. Then our aim is that it is a tedious process. We have to take these n objects one by one. We have to see that which this object belongs to which group or which clusters. How will you match it? We are having a centroid. Centroid here, it is nothing but some mean. We'll be comparing. Comparing here in the sense that what? It is nothing but a distance metric. In mathematics, comparing is a distance metric. We're just finding the distance metric. We're just having the minimum distance. We'll be just putting it in the particular group, right? Calculate the centroid. Next, once this is done, from that, now first step is that we have obtained some clusters. From the clusters, now we'll be finding the mean. Again, we'll be calculating the centroid, right? First, arbitrarily we have selected the centroid. Then we have done the distance metric. Then again, we are calculating the centroid. Recalculated. Then with respect to that center, we'll be just finding the steps 1, 2, 3, repeat, and we can stop when the first cluster, that is when it is grouping again the same pixel is grouped in the same cluster, we can stop, one criteria. Or we can give some other iteration numbers, number of iteration, this much iteration numbers we can stop, or any other parameters that if you want to stop it, that you can stop. And this is the actual k-means algorithm. Okay, so this also I have taken it from the source. This is another one source, that is from this data analytics, right? As it is good that you can able to graph easily. That's why I've taken it from enough, plenty of resources are available. That's why I have not again prepared this. I have taken it for your understanding. Okay, so I have represented here. I am giving courtesy to that. Okay. So now you see that we are having objects with two attributes. Now this is data. Instead of image, I have shown you a data which has two characteristics or two attributes here. And the distribution of these attributes are plotted in this. So the dimension is 2, so it's easy for us to visualize. But if it is an image, it is very difficult to visualize. That's why I've taken this, right? A1, A2, now you see that this is the feature with attributes up to 12 maximum. So now we had, now this distribution is like this. There's A1 and A2. Now we have to use the k-means algorithm to cluster these two groups. This is our attribute. Now we have to go for segmenting these things, which group it belongs to, how many such data or how many such informations are available, similar informations are available, which can lead to further understanding or recognition or whatever applications we can go for, right? So now I'm just having this red color represents now. I have told now when we are going for this first step is that how many clusters, number of clusters. So if there is 3 clusters, then 3 mean or centroids or center of gravities need to be arbitrarily selected. So it is the red color represent that these 3 centers are get selected. Okay. So how many clusters now in that data points K3, right? The 3 centroids are shown C1, C2, C3. So A1, A2, that's what is the attributes for this C1 for this value from this, right? They have taken this thing. So from the data, they have again reproduced here. Cluster 1 is having an attribute of this. Cluster 2 is having attribute of this. If this is an image or a pixel, this will be represented by pixels. Okay. Next, what norm we are going for? Different metrics. Here it is L2 norm, or we'll be having Manhattan norm, distance metric, Euclidean distance, anything we can go. So distance measure, as the distance measure, this is here. D1, D2, and D3 denote the distance from an object to C1, C2, C3. So for all the attributes, we have to calculate the distance from this for each attribute, because this is the cluster centroid, right? So assignment of each object to the respective centroid is, now you see this distance metric. So this is the attribute, 2 attributes. Now 3 clusters. So how many distance vector or how many distance values we'll be getting? 3, right? So now it's a matrix. Now you see this, we are having which one is having the minimum distance, this distance, this D2. So for this attribute, the cluster 2 is showing minimum distance. So this is act as a cluster 2. We have segment. Remaining things, this is 3 minimum, so it is 1. Now coming to here, this distance is very high, this distance is very high, so this distance is low, so we are having this is grouped as 3. Now you see this, we are having initial cluster with respect to the table. Now we are having how many 3? This is 1, 2, 3, 3. 3 points are only in cluster 3, and 1 point, more points are for cluster 1, and minimum points are in cluster 2. Okay, 4 points are in cluster 2. Now the question is that this, whether we can have this fine tune in this or like that, that is also a thing, but because it is nearby, right? It can be, maybe this cluster can have, because other points are somewhat far away. This is maybe this can fall into the clusters or like that, right? So the calculation of first, that is first iteration. This is first iteration. It's not over. This is first iteration. Now next our aim is that first we have initially randomly selected this centroid, right? Randomly selected this centroid. Next, we have to recalculate the centroid so that our segmentation algorithms will be fine-tuned. So you see that I have told the computing which is required for this k-means. What are the different computings or number of computings which is required for this k-means? First is that based on our random, if you are having some prior information about the image or data, then we will be easily predicting about the number of clusters. If I am saying that, what do you mean by that? Suppose if I'm having an image, only a passport size photo of a human being, right? So passport size photo will be like this. So we can say that now I want to segment only this portion. I want to segment only this portion. Remaining portion I don't want. So how many clusters I have to have now? Yes, from the audience, whether your mic is possible to unmute or just use 2. Yes, good. Okay. Some interactions we can have. Okay. Yes, thank you. So we can have 2. So the number of clusters is 2. Now, suppose the image size is some 64 cross 64. How many cluster centers I have to select? C1 and C2. This C1 and C2 may be one of the pixel from here and another one pixel from here, right? We have to group it. It is having some features. This is having some features. Background. Suppose if the background is white, fully white, it is very easy that what it will be fully matching with the cluster one, right? If it is white means all the pixels are 255. If the background is white, high intensity 255, right? But if it is not white, background is not white, then some amount is required for us to recluster. Iterations will be more then, right? So it will be easy. So now you see that C1, C2, every time when it is calculating distance D1, D2, so we can say that it is having C1, C2, so distance metric D1, D2 for the entire pixels. It has to calculate the distance metric. What is distance metric? If it is a Euclidean distance, it will be square root of x minus x1 square plus y minus y1. So square is required, then subtraction is required, then square root is required, each and everything. So somewhat it is tedious, but every iteration, how many iterations it will go. But we are using this, but some advanced level k-means algorithm has come, but now we can say that we have to calculate now. So that is the computing complexity. Okay. So now we have to change this mean, because now you see that there is a border in which it may fall here or it may fall here, or we can make a cluster like this also, right? Like this also, or a cluster can be like this also. So how it will make it? Now mean has to be changed, right? New means the calculation of the new centroids of the three cluster using the mean of attributes. So this figure 16.3, I have just taken this from this data analytics, the book presented, right? So you can ignore this. This is a figure. Okay, this is the figure. So calculation of new centroids. Now you see C1, C2, C3, right? From this, we can say that three cluster using the mean of attributes value of A1. What are all the values here if it is present? From that, we'll be calculating the mean, right? So we can say that different, this is A1 and A2. From A1 and A2, we are calculating the means. So we have got now 4.6, 7.1, 8.10, 6. Some values, different values, right? From that, we have got the new centroid C1, C2, C3. So the calculation of new centroids using the mean of attributes, the cluster with new centroids, right? Now the new centroid, earlier this is the old centroid. The pixel itself or the data itself is the random selection. Now you see that it has moved like this. It has moved here and this has moved here. So this will be having less distance for this, right? If this data center is moved here, this will be having less distance. This data center is moved here, so this will be having far away distance from this, right? So initial cluster with new centroids. Now you see that we'll be having this, right? So this has given a revised cluster. Then again, if now we have given only 3 clusters, with these 3 clusters only it has to. Again, if I am saying we will be finding the mean of for this reorganized clusters, and again if I am applying the distance metric and I am finding that if all the pixels of the previous this group, this is second iteration, right? This is second iteration. When I'm doing the third iteration, if all the pixels of group 1 or cluster 1 again falls on cluster 1, and if all the maximum pixels of cluster 2 it falls on cluster 2, like that, then we can stop iteration. This is one of the criteria, stop iteration. It's not necessary that we have to do like this only. We can have any mean square errors, we can have, so any metric. So we can see those metrics also, right? Because the evaluation metric or performance metric to find the cluster sizes, to find or evaluate or validate this flow is very much important when we are defining any algorithms, right? So this is whatever I have told, that termination criteria, anything we can follow, right? So whatever I've explained, it is there. So now we have ended up with the cluster after second iteration, right? Comments on this k-means algorithm produces only one set of clusters for which user must specify the desired number of clusters, right? If it is a best guess, then that is no problem. Choosing the best value of k, if we have prior knowledge about that, then that will be good, right? For high dimensional data, it is very difficult. If you are scatter plots, or if you're going for our own images also, if you're plotting also, we can't get much how many clusters are like that, right? But if it is color based or feature based or texture based like that, somehow we can bring this. So now you see that for the possible number of clusters is hidden or ambiguous in image, audio, video, and multimedia clustering applications. So there is no principal way to know what the value of k. We may try with successive value of k starting with 2, increasing, right? Like that. Normally k is what is the condition for k? K has to follow this heuristics. This is through the experiment people have found out that k should be always rooted. So now if it's 64 points, if I'm having k can be maximum of 8, we are saying. So this is okay. So now we are having an index or the metric, which we are saying it's some square error, which can give some details about how many cases we can select for the particular data. Okay. So using this objective function, people will be defining the clusters. So usually there is some objective function to met as a goal of clustering. One such objective function. Anyway, the objective function earlier is what distance metric. The distance metric has to be reduced, right? Then we will be selecting the particular pixel for in that particular group. So here we are having a metric called sum square error. What is the sum square error? I'm assuming some k clusters. That means we are having some cluster groups, right? This is this. So this is the cluster center. This is the actual pixel. This is the cluster center. Now I'm subtracting and taking square. Then the value will be, if this is similar, the value will be less, right? So for in a particular cluster, for all the pixels, right? I'm just finding the sum square. Then for each groups, right? For each groups, I'm just making it. In a particular cluster, we are having some pixels. And for each cluster, we are just doing that. So x minus c denotes the error. If x is in cluster Ci with cluster centroid C, okay, XICI denotes the error. That means it's known. Cluster, this is the value. If x belongs to C, this value will be minimum. So x minus C denotes the error. Usually this error is measured as distance norm like L1, L2 or cosine similarity, etc. Sum square error. Now you see this. Now if I'm just finding if k is equal to 1, cluster, 2, 3, 4, 5, right? So I am getting for the data what I have shown earlier, it is giving the sum square error. Sum square is a metric we are using 62.8 if it's 1. If it is 6, 7, 8, it is giving 9, right? So we can say that now with respect to this observation, we can say select either k is equal to 3 or k equal to 4, right? Smallest value of k, because when we are going for highest value of k, then computation is also high computing. It may result in overfitting, right? If k is equal to n, then we are sure that the small scale error is equal to 0. The cluster, that is another, that means we can say that it is overfitting. So we shouldn't allow them to be overfit, right? So we can say that we can use certain metrics also to find the number of clusters. So just to show you the k-means example, we are having an image. It's a old one archaeological image which is shown, which is having different colors, and when it is segmented, so all the golden colors with this thing, based on the color, maybe this is segmented, right? This is segmented, this red color portion is segmented with that, right? Top roof is segmented with 1. So how many clusters we can have in this image? How many clusters for this image? 1. Here we are having 1, 2, this is 1, this is 2, this is 3, right? This yellow is 4 and this is 5. So this we are having 5 clusters. So similarly we can have, so now this K means a grouping we have segmented, right? Once we have segmented, it's easy for us. How we will segment the image? Using the, anyway, next session you are going to see about hands-on. We'll be making a mask, whichever which having this values, in this value we'll be making at 0 or 1. Then we multiply that image with this or with this, then we'll be getting the respective portion, right? That we are calling that as masking. Using mask, we will be just getting the respective data for further application. So this is what I have shown. This k-means algorithm. It's also having how we will be fixing, that we can see. Okay. there are problems in k-means, okay, that we will come later. Then we are having algorithms called another one variant in the partitioning method. These are all we are saying clustering partitioning methods, okay. K-Medoids algorithm. Medoids here represents that the data itself will be taking initially as a center. So now you see that K-means algorithm, if the data variation or the variance of the data, or if a group of data we are having, if the variance of the data is huge or the value of the data is extremely very large, it may very difficult to group it, so may substantially distort the distribution. If it is smaller, distance is smaller or somewhat acceptable level, then groupings will be easy. Otherwise, it will be having some problem, right? So this effect is particularly shown badly due to this use of sum of squared error objective functions. We have shown if the variation is large, then in the sum squared error, it will show that, okay? So now we can say that K-Medoids algorithm aims to diminish the effect of outliers. So now we can say that what is the basic concept of this algorithm? So select an object as a cluster center. This is very much important. Select an object as a, earlier it is not necessary. In between the range also we can select. Select an object as a cluster center. Okay. So one representative object per cluster, instead of taking the mean value of the objects. Okay. This cluster representative is called Medoid or simply Medoid. Okay. So same thing, initially random set of, here also randomness coming. You might have studied about different, you have heard or you have referred many algorithms for clustering. The fuzzy or k-means clustering, it is having initially we have to select the objects, clustering objects. For automatic selections, we are having different algorithms. Okay. We have the advanced k-means algorithm is the fuzzy c-means algorithm. In fuzzy c-means algorithm also this initial randomness is required, but selection is required, but we are having algorithms to automatically, based on the nature of the data, by having some statistics, imposing the statistical characteristics on the particular data, we can select the objects first, initially random centers, okay, or centroids. So this is each step, all the objects from the set of objects which are not currently Medoids are examined one by one, because one of the object we have selected as Medoids, then we have to examine the other pixels or the objects which is not considered as Medoid one by one. Okay. So here, what is the objective function which is used is that sum of squared error is used in the previous. Here, the objective function which is used is that sum of absolute error. So instead of square the distance, here it is x minus cm. So here the value is somewhat higher. When we are just making it sum of absolute error, it will be higher, because earlier that is square, it is higher, right? Cm denotes the Medoid. M is the set of all Medoids at any instant. X's and objects belong to set of non-Medoid objects. Okay. So now you see that by looking all pair of Medoids, non-Medoid objects, and then choosing a pair that improves the objective function of clustering, which is minimum. This, if it is minimum, then that will be selected as the Medoid. So this will be again we are saying. So we are calling this algorithm as partitioning around Medoids. Okay. So K-Medoids algorithm is also known as partitioning around Medoids, because we are just saying whether this Medoid, whatever we have considered, is an exact center. We have to look, or we have to reconstruct, or not reconstruct, whether we have to exchange this Medoid with some other Medoids to get the successive. We are saying that sum of absolute error, which is less, which is the objective function we are looking. That's why this algorithm is called partitioning around Medoids. Okay. So for example, now you see that there are 12 objects. This is also a one-dimensional data. So we are having 4 clusters. So now from this 12, we have taken Medoids. The image or the object itself is Medoids, right? We can calculate the sum of absolute error. Many ways to choose non-Medoid object to be replaced any one Medoid object. One of this is, suppose if O5 is considered as a candidate Medoid instead of O4, because which gives the lowest this SAE, then we can replace this O4 with O5, right? Instead of mean. Now you see this. This is the cluster with O1, O2, O3, and O4 as Medoids. Then we can say that we'll be going for now again, which is replaced by this becomes the new method. Likewise, we'll be going for, this is also an iterative procedure. We can stop when we are having it is replaced again and again in the same cluster. We can stop the iteration procedure, or we can fix the number of iteration, maximum iterations. If it is gone, we can stop it, or we can fix a threshold for the SAE, sum of absolute error, and we can stop it. It all depends upon the applications. Okay. So this is partitioning around midwives. This is one type of clustering. These are all simple clusterings. If you're sure about the event, people will be using. If you're not sure about events, in the sense, what I mean is that the data sizes and all those things, before adapting these types of clustering, we have to use some other automatic or intelligent techniques to select efficiently the number of clusters. And after that, if you are applying, and if you're not bothered about the number of computations, it's okay that we can go ahead with that, but this will be doing fine. Okay, so this is whatever I have told. This is there with this thing. So this slide, this I have put it is that comparing k-means with k-method. K-method method is more robust than k-means in the presence of outliers. Outliers here, it means that data variation is huge. There is a huge variations between the data, right? So it is less influenced by outliers than a mean. Time complexity of PAM, that is, this will be for each iteration, PAM, this is taking k is number of objects, right? N minus k pair of objects, for which a cost of OI, OJ. That means each time it has to compare, right? Calculating the cost during each iteration requires that it has to be calculated for all non-medides also. So we can say that it is come out with a generalized function that the total time complexity per iteration is this. So the total number of iterations may be quite large. Does not scale well to large database because of its computation complexity. If I'm not bothering about computation complexity, we can go ahead with this. Okay. So this is also this adapted presentation. You can go ahead for more reading with these types of these papers, whatever I told. So this k-means challenges. Next, we can come to this k-means challenges. This is the simplest algorithm we have seen. Okay, that's fine, but it is having some challenges we are having. Can be a local minimum. That means the optimum value we are saying that is, right? When we are just finding the deviation between that, we'll be getting some minimum. But does not always find the global minimum of objective functions. So the objective functions, when we are just minimizing, if I'm getting a minimum, proper optimal minimum, then that will be good, right? So now you see that there are in k-means there are different variants we are having, different ways to initialize the means, different stopping criteria we are having, and dynamic methods for determining the right number of clusters for the given image. Okay, shall I proceed or you need break? Because you are 9:30 onwards, you are there on the, I can proceed, right? So let me have some discussion. The first session of that, have you had anything on image segmentation, the basics, image processing? What are the things you have learned, you have come across? Participants, are you on live?
Ma'am, I have a doubt, ma'am, actually.
Yes,
Ma'am, in k-means clustering, ma'am, suppose if the distance remains the same for two centroids, then what will happen actually?
Distance center with respect to that, if I'm saying, you're asking that?
Yes, ma'am. Previous slide,
So
ma'am.
now,
If the
okay.
distance during first iteration, ma'am.
Shall I go there?
Yes, ma'am.
Ah,
Ma'am,
so now,
suppose D1 and D2 remains the same for any one of the rows, and then it will be assigned to
then
which cluster?
you can opt any one of the thing you can opt.
Okay.
Then that means if many of the objects, if it is coming like that means, then it means that that is not necessary to have more clusters. Okay.
Okay, ma'am.
Then you can merge also.
Yes, ma'am. Yes, correct.
Based on the statistics distributions. Okay. That's
Okay.
why if you're having a prior knowledge, then we can easily define the number of clusters, then it will be giving a correct output. But only thing we have to trade off is the computation complexity. That's why still K-means cluster people are following, right? So many of the distributions, if it is known, for that it is standard, people are using that. But in many of the applications like our image processing applications and all those things, many data we don't know that what type of pixels or what type of things are which is available, very minute details we want to segment those things and all. Then we can't go for directly by giving clusters, or we have to go for trial and error method to give initially 2. That's why I have told 2, 3, 4, 5 that play, and we can play and we can do that, right?
Okay, ma'am. Ma'am, should we give any stopping criteria, ma'am, to stop
Yes.
this?
Yes, we have to give stopping criteria based on the metric. So here the metric we are saying is the distance metric, or what I have told is that suppose it is not coming. The distance metric is that now you see that we have just clustered 3 clusters. Again, when I am finding, as you saw, distance metric, when I am getting the matrix distance metric, shall I go ahead? My connectivity has gone. Yes.
Yes, ma'am, we are able to hear you.
Yes. Thank you. Okay, my in between my connectivity has gone. That's why I asked. Okay, then shall we proceed? Okay, so 2 algorithms we have seen. Okay, middoids and k-means clustering, right? And so many, still we can speak about so many issues of k-means, but I have just given focusing on the basics and some issues, major issues. But you can go ahead with the literature. Lot of advanced algorithms has come. Okay. Before that, this thing I'll be going for. Okay, this weekend. So K means variance. Now we are going for a probabilistic based method of K means. Expected maximization algorithm, EM. Okay. So instead of having the cluster centers directly, we are selecting. We are going for a probabilistic formulation. So we are just finding the probability density function. And based on that, we are just selecting that how it can be. Okay. So we will be just dealing with that now. So what is this EM algorithm? So instead of treating the data as a bunch of points, assume that they are all generated by sampling a continuous function. Okay. So that's the probability distribution function, right? Continuous function. So instead of treating the data as a bunch of points, we are just giving an assumption. So this continuous function, it should have all a particular distribution function. So this function is called a generative model defined by a vector of parameters theta. Okay. So here we will be normally going for Gaussian distribution. So this is the idea behind that. Basic idea is that instead of considering a discrete point, we are just obtaining the data points itself, or generating the data points by sampling a continuous function. We are fitting the distribution on the particular data point, and from that, whichever falls on the particular data points, we'll be just sampling it and getting the data. right? So the function is called generative model defined by a vector of parameters theta. So this is a parametric model, we can say. So now here also the step is required as initialize k clusters. Each cluster is represented by its mean mj. Okay. Estimate the cluster for each data point. That means we are saying that whether this cluster belongs to that. We know re-estimate the, so this is the same thing. K means we are saying. Now, when we are going for the next, so now you see this, K means we know these 2 points are there, 2 clusters now it is having. These 2 points are separated easily, but these 2 points, where it goes, where do the red points belong? So this is, now we are going to apply this probabilistic method to easily get into that. Right, this can belong to this or this can belong to this. From human being, we will be saying that this is nearest to that, so it will go here, this here. But not always true, we can say, right? So where do the red points belong? So now you see that instead, earlier what we have done, initialize k clusters and we have mean, right? Then we are just finding the distance metric between the cluster point mean and the respective pixel. Here, all are probabilistic. Distribution, you see that this is the distribution. This distribution is having mean and we'll be having variance, right? Mu j, some is sigma j, and we are saying this is the probability p of cj. This is the cluster for each cluster j. So we are having a probabilistic value. Now, this is the initialization we have to do. Iteration step. Now, what we are doing, estimate the cluster of each data point using the conditional probability. What is this conditional probability? Xi is known. Which cluster groups it belongs to. That is the probability of Cj by Xi. This is expectation. So this I'm calling it as expectation. Estimate the cluster of each data point from the distribution. This is the distribution. Right? So we can say now it has mean and variance. So re-estimate the cluster parameters. That is, we are calling it as maximization, expectation maximization, EM algorithms. It is computationally tedious, but now we are defining a generative model. Okay. Then for using the generative model, we are having some data points. Using the data points, we are just finding the cluster, how many clusters mean that we have to give. Estimate the cluster, then we are maximization for each cluster, right? So now you see that each cluster Cj is represented by a Gaussian distribution, normal distribution, variance and mu. For each cluster Cj, initialize its mean, variance and weight. One weight vector is there. So now this is now 3 groups it is shown, which is having a variance of sigma 1, mean of mu 1, right? Which is having a weight, that is the probability. So alpha 2, alpha 3, that means for the cluster C1, C2, C3. So now see this is the variance is less. This is somewhat high, right? This is actually, we are having variance is less, but the data centered around here. So these types of curves we'll be having each clusters which. So for each point xi and each cluster, I have told you, right? This is the base, this equation, this probability formula we know. So this also we know, right? So why do we get P of xi by cj? That means we record here P of xi by cj to get xi cj. Cj cluster, we should know that. So initial clusters, from the clusters, we have to get the approximate data of xi. So from which distribution? Probability density function. Using this distribution, we have to find. How will you find? Already we have defined, if this is a cluster of C1, we know what is the value of U1, which belongs to all the pixel values we are saying, right? Xi, all the pixel values will be just finding this P of xi by cj. Then alpha j is equal to P of Ga from the current parameters of cluster Cj we have to find. So these all probabilistic models we have to get a distribution from the probability density functions. We'll be finding this. So this is a probabilistic model. Now you see this, having computed this for each point and each cluster, now we have to find the mean, right? Variance and weight. So every time computation is tedious, we have to find this. This is available, right? This is for how many distributions we are having, variance and all. We have to find the variance. This is called maximization, right? Now you see what is how this procedure goes for clustering. Input, right? This is for multi-dimensional. Why I've shown this mean, now you see this, we are having a color image, which is having the attributes like this, x1, x2, xi. Each pixels will be having 3 pixels, right? If I'm having a grayscale, then each pixels will be having only 1 pixel, right? And we can have cluster parameters. What are the input estimation we have to go for EM? First, we have to see how many clusters. Suppose if I'm having C clusters, I have to define the variance. Then the weight parameters, I have to define the weight parameters. 1 minute. Okay.
Ma'am, participants, can you hear madam?
Yeah, I have muted on phone call
Okay, okay, ma'am. Okay.
because some examinations going on. I'm coordinating. That's the problem. Okay.
Okay, ma'am. Sorry.
Sorry for the interruption. So input estimation is probabilistic method. You see that then we are going for classification results. The output we will be having whether this xi belongs to cluster 1, cluster 2. This only we have to find. So these are the steps that we are going to follow. Since it is probabilistic method, it is based on a distribution function. It's continuous functions, right? Somehow, as compared to the normal k-means, which is hard bound k-means algorithm, which gives the may fall into some local minima problem, right? We'll be getting some global minima or we can say that optimal value using these steps of EM algorithms. Okay, so this is just a procedure.
My voice is not audible, ma'am.
It is not audible.
Sir, yeah, understood. Please hold for
For the
some
past
time.
minutes, it's not audible.
Yes, ma'am. It was not audible for last 5 minutes, madam.
I have muted and I am keep on speaking. Okay. Sorry.
And that
Lot
is
of interruption when
no
we
problem.
in online mode. We have to go for multitasking. That is the
It's okay,
problem.
ma'am.
System is
It's
also
okay, ma'am. It's
expecting us to
okay.
have
Just
multitasking. Okay.
it's okay, ma'am.
Sorry.
Yeah, please.
Okay, let me
No
go
problem.
ahead.
No problem.
You have to
Please
immediately
proceed.
respond to me if you couldn't, because I won't be more than 1 minute. I won't be silent. Okay.
No, ma'am, what I thought was like maybe as you did before you muted, maybe you
Okay.
had some work. It's fine, ma'am. It's fine. We will let you know, ma'am. Kindly
Yes.
proceed.
Yes. So what I have told is that full EM algorithm, this multidimensional, it not only for RGB, we can have any features. Suppose color, texture, different features. If I want to, I have selected in my image, that also I can give as input to this, and I can use these algorithms to proceed to get a good segmentation based on color, texture, feature. Okay, but thing is that you see the computations, all probabilistic calculations it has to do. Okay, so that if you can able to manage, then no problem, that it will be giving as compared to the k-means, this will be giving good. So here also we have now these types of segmentation. Normally the main application when we are going for probabilistic methods, blob deduction, we are saying one type of technique, blob word, sample results. Now you see this is blobs, we are saying blobs, giving good blobs. Okay. Now I'm not going into the mean shift. I'll come later. Mean shift algorithm. It's also one type of k-means. Okay. Normally followed in. Now I'm going for the next type of segmentation. Segmentation by graph partitioning or segmentation by graph theoretic clustering. Okay. Graph based clustering. So what clustering now, it can be seen as a problem of cutting graphs into good pieces so that it can segment the data easily. Okay, so this image has to be first represented in a graph. Then we have to use graph cutting methods to cut the graphs based on some statistics, and we can make a group or cluster or segment. Okay. Now you see how an image is represented by a graph whose nodes are pixels or small group of pixels. Okay, small, instead of a pixel, we can have a small group of pixels. We'll be calling it as super pixels. Super pixels always means group of pixels. So now I have just shown, first you can see here, not there, this image now it is represented as a graph. Okay, how many pixels are there? To show you 3 cross 3 pixels. Each pixel is this. This is called vertex or edge. This is connected to this each and every pixels through a link. This link has its own weightage, okay, based on the similarity, right? So this is the vertex in a weighted graph. So this is vertex. It has a weights. The weights on the edges between the elements are large if the elements are similar. If the weights are higher, then these two pixels are similar. If the weights are low, then these two pixels are missing. This is the thing, simplest thing. Based on that, we will attempt to cut the graph into groups. Okay. So now you see this. This is CPQ. This is nothing but a distance vector. We can say a similarity measure, or we can say a weight between PQ. Right. So this is pixel, which is C. C, if it is higher, then there is a similarity between this pixel and this. If C is less, then we can say that it is not. So the goal is to partition the vertices into disjoint sets so that the similarity within each set is high and across different sets is low. Okay, that is the concept. So now I am having 2 sets. Now you see, this is one graph, this is one graph. Now this is connected to here. So if this is very far, this weight will be less, so I can make a disjoint cut here. So how efficiently I will cut it? How the cut set will be, or after cutting the graph, which is a proper cut, that is very much important in cut. Okay, so before this, okay, let's see. So segmentation by graph cuts. Now you see here we will be having another one image. I have shown same thing. Using graph cuts, we can make these things, segments, right? Along with that, some segments also it is considering, right? This is one segment, this is one segment, segment like this. So now you see the segments by graph cuts. Now these two graphs, this is one graph cut, another graph, another graph. Okay. So delete links that cross between segments. Easiest to break links that have low cost similarity. Similar pixels should be in the same segments. Dissimilar pixels should be in different segments. This is the concept. So now we are going for the concept called minimal cuts. Okay. So now vertex, you know, in between the vertex we are having a weight matrix. So in the weight graph that we will be representing the weight using a matrix. By seeing the matrix, we'll be just using some metrics. We have to see which one will be maximum, which one is minimum. We will be throwing it away. After that, the matrix will be divided into 2 or 3 or 4 based on the cut. Okay. So how we will be doing that? So now you see this. This is let G is equal to V of V be a graph. Each edge U comma V has a weight that I have told. Graph G can be broken into two distant with node sets A and B by removing edges that connect the sets by using the cut. Okay. Summation, that means we are having U belongs to A, V belongs to B, cut W of U comma V sum, which is minimum. That is important. Okay, cut W1, W2. So now we have cut it. Minimal cut favors cutting of small node groups. So this other, the famous graph cut method, right? So that's why it's given. So it is proposed the normalized cut. It is having a normalized value. What is this normalized? This is the sum of all weights. How much is A connected to the graph as a whole? Okay. So normalized cut of AB. So now example of normalized cut, you see that normalized cut of AB. That means we are having this value, cut of A comma B. Okay. By 21 plus 3 by 16. This value we are just taking is as a normalized cut. So now this is low, this is high. But as compared to this, which one we will cut, that we have to see. So this I have already told you. Again, same thing is coming. Now another one thing that we can say is that, okay. So this is up to this, what it means is that now you see, once again I am consulted. We will represent the images using graphs. Then we are having vertex with weights. Then we have to find the minimal cut. Minimal cut in the sense that cut of A comma B is possible when the weight matrices we are having is high. Then we will be having similarity. We will group it in that particular graph. If it is very less, we will separate it out. Again, you will be doing these iterations. If I'm having more number of graphs among those graphs, then I will be seeing what is the weight. So at last we will be end up with, if there is no cut possible, then we will stop it. So this is the method. It is also, we can say, yes, this is the method in which it has followed. And nowadays, you know that this graph theory, image processing using graph theory plays an important role. I don't know whether you have referred things, because so many papers has come, image processing using graph theory, because the mathematics which they have used using these graphs, defining as a graph and applying operations based on graph theory is also emerging, right? Not now itself, now only it's emerging, for the past 10 years like that, when we see lot of graph theoretic possible. So clustering also has evolved. So many advanced algorithms has also come for clustering using graph theory. Okay. So this is thing. Next we can go for this problem. This is same graph theory only, but what actually it means. Okay. Graph cuts into an eigenvector or eigenvalue problem. Okay. What do you mean by eigenvector or eigenvalue problem? Now you see that we are having cluster. Okay, this I'm just explaining eigenvalue, how we will formulate the eigenvalue and eigenvector problem as segmentation. Okay. There are k elements and k clusters, right? Or n elements and k clusters. Okay. Cluster I am representing using a vector, right? A cluster I am representing using a vector with k elements. So I am having cluster, K cluster. I am representing the cluster using a vector because we know that eigenvector, eigenvalue is a vector problem by a vector with K components. Okay. Now what we are doing is that these elements, we are allowing these elements to associate it with a cluster using some continuous weight. Okay, weight is now continuous. We are associating these elements to this cluster using some continuous weight. Okay, so now what we will do, how we will associate that with the cluster? If the weight is weak, then its association will be less. The weight is huge, large, then the association will be, right? This is the concept. Now I have defined now a vector, right? Now you see that a good cluster, we know that it is strongly associated with a cluster having large values of this weight. This is a matrix. So now I am representing this as a matrix. Okay, this matrix, if I am saying, is some matrix. That means not this matrix. I am just representing one matrix which has a context that, right? This value A, I am just making it that based on the relationship between this element and cluster, I am having a matrix A. Okay, so this A is nothing but we can say that we'll be having, suppose I am having an X function. I am just linearly relating this X with Y, then I am having a transformation function A. So now see A into X. Suppose if I want to make X means, then I am saying that I will be getting some A inverse of this value with Y, I will be getting, right? So this A I am just defining here. So A is nothing but a type of matrix which represents that based on this weights, right? It will be, we'll be having a particular transformation matrix A. So now you see that we'll be having now weight. This weight and A are now related, right? This weight is the input. Weight and A are now related with to give some outputs, right? So we can construct now, you see, weight function with a strongly associated some matrix that is A into W. What do you mean by this? I'm formulating this cluster problem, considering this as a vector. I'm just formulating through to a eigenvector problem or eigenvalue problem by defining a specific matrix called A. What is this matrix? This is nothing but we are saying that in context, we can say that this is the affinity matrix between I and J. I is nothing but the cluster, right? With the element I and a cluster J, we can say. So affinity matrix. What is W? W is nothing but we can say that it's a weight association of an element I with cluster. What is this W? W transpose this W. So if it is I with a cluster, then W can be J with a cluster. W is nothing but the weight matrix which represents the weights between the element I and the cluster. This weight matrix is nothing but between the J and the cluster. What is this A? A is nothing but the affinity between I and J. Affinity between I and J, not with the cluster, but based on this weight, we are making it. Right? So now once we had this problem, this thing, then we can calculate the eigenvalue. This objective function can be easily formulated as a, right, as a eigenvalue problem, right? So how we will be, we have to, this W3AW, we have to maximize this. We can obtain a cluster by choosing a set of associations. That means the weight vector, right? We can obtain a cluster by choosing a particular weights that maximize this objective function. This function has to be maximized. If this is maximized, then that particular element belongs to the cluster. So it is reformulated. In the function is now reformulated. After it is reformulated, then this can be used as a eigenvalue segmentation using eigenvector or eigenvalue problem. Similar way in graph theory also it is done. Okay. So here when it is formulated, we know now WTAW, then eigenvalue problem lambda into WTW. This is the Lagrange's weight. That means Lagrangian function. We just maximizing, right? But the weight matrix always it is an identical. That means WTW is equal to 1. Under this condition, we'll be formulating this. So this is what I have mean is the eigenvector based segmentation. Okay. So this will be maximizing to get the cluster. So or we can say we'll be having A affinity matrix into weight matrix is equal to eigenvalue into the weight matrix. This is the thing we'll be getting. What do you mean by W? And what is the W is a now from this, what is from the mathematic point of view now tell me? W is a eigenvector, right? Eigenvector of A. W is an eigenvector of A. Okay, from the eigenvector we can calculate the original value, right? Yes. So this is the thing. So now you see E set of weighted edges. Length Di is the sum of the weights from node I to all other nodes. N cross N matrix D. That means D is the diagonal matrix with D on its diagonal. That is the sum of weights D on its diagonal. N cross N symmetry matrix with all the weights. Okay. So now we can say we'll be having let X be a characteristic vector of set A. So Xi is equal to 1 if node I is in set A. If Xi is equal to -1, otherwise that we are just making a characteristic vector for a set node or a cluster, we can say, right? So we are just defining now with respect to a continuous function. That means we are approximating this X, right? And we'll be getting Y be a continuous function. So we are defining this using the eigenvector problem. Now you see that we'll be having what is D here? D is the diagonal matrix that we know. Trace W is the symmetry matrix, which we are getting it from the weight matrix. Then lambda into dy. So y is nothing but this function. We are just making it. This is the distance metric we are having. So for the eigenvectors y and eigenvalues lambda, we can solve this function. So this whatever I have told, this is easily we can say that I'm having an affinity matrix, that is the D matrix here. I'm having a weight matrix that is same W, right? Using this A, W transpose W is my function, not function, it's a matrix now. Now I am just defining eigenvector problem. I want to find the eigenvalue, eigenvector. So for that, I'm just defining the eigenvector, eigenvalue by maximizing the Lagrangian function, right? From that, I'll be getting eigenvalue. From the eigenvector, I can get the output, y or x. So anyway, people have found, or using the mathematics, they are applying these things, different algorithms has evolved. And this is from the She clustering from her page. Okay, so based on this type of graph cut, or we can say the graph cut based eigenvalue, eigenvector problem, right? So this is segmented. These are things that you can see in the MATLAB based things also, it is available. Okay, but graph cut is not there, but you will be having, people have floated many MATLAB algorithms for graph cut also. You can get it and you can perceive the algorithm, how mathematically it is applied. That will be good. Even though what I'm explaining, it's not very much clear to you, right? I'm not having a tutorial for the eigenvalue problem. Okay, so but if you can make a matrix and if you are easily explaining that, that will be very good, that for an understanding. Okay, so the problems with graph cuts need to know when to stop, very slow. That is there, but if I'm having any fast methods that we can calculate these values, then we can, okay. And problems with EM, this is, it can enter with local minima, need to know number of segments, need to choose generative model. These are okay, K-means also. But here in EM, expected maximization, what generative model? We are going for the Gaussian models, right? So which one is apt? Which continuous functions we can map to the data so that we'll be getting the generative model. Okay, so this also we can. Next, in the initial stages, when I'm explaining about different types of clustering, I have told about the hierarchical clustering, right? This we can say that divisive clustering, agglomerative clustering. There are two types of clustering which we'll be having, that we are calling it as the divisive clustering or the agglomerative clustering. Okay. So in this method, now you see this, whatever diagrams I have shown here, we are having some elements or symbols which is given there, right? So when we are having some symbols there, what it is PQRST. Now it is now divisive clustering. Construct a single cluster. Now we are single cluster, right? Next is that some using some conditions, split the cluster that yields to 2. Okay. Then that means how will you cluster it in the two? Interdistance. Interdistance, what we will use? Distance metric. Again, we will see that among this, is there any difference that we have to make it, right? Again, we are just going for this. So now PQRST, right? Each one may be some group of pixels, maybe. Now this will be considered as output as 5 groups. Okay. So this is now you see, first we are having divisive clustering or clustering by splitting. This is, we are saying that clustering by splitting. Okay. But we can say that when we are having less number of data, these methods will go good. But if I'm having more number of data, then this methods normally it's not used, we can say. Okay, this is what I have told is the not used in the sense conventional method of clustering. So we are also having methods which one of the methods here I am explaining is that hierarchical clustering. Initialize, assume the maximum number of groups. So this is very much important, how many groups we are having. Okay. So now we see that we'll be going for diagonally average the groups as described previously. That means this is the groups. Okay. So we are going to average that. Next, we are saying that compute the correlation between the groups. So the correlation factor now it is again the distance metric. The distance metric here it is nothing but this is cosine similarity. So 1 minus this inner product norm of values, this thing we are just finding. Combine two groups for which D is minimum. Now you see that only thing you have to understand here is how efficiently we can make we can use metrics or objective functions or distance functions. Okay, because all clusterings are having only mathematical formulation. It's easy for us to use by just selecting the function. But if we are modifying the objective function and the distance metric, then that plays an important role. Okay. So based on the applications, based on this segmentation also, we can't say that this technique can be used for this. This can be used for any type of images like that. It is also, we can say, localized. If I'm taking a particular image and I'm segmenting, if the particular distance metric not works, right, I can change the different distance metric or objective function and I can play with that and I can get the efficient data. But it's not necessary that it will be suitable for the other type of segmentations also. That's why when you're going for medical image processing, we have to be very careful that what type of image segmentation we have to use it to efficiently extract the image portions which is required for further deduction, for further anomaly deduction, whatever may be, right? This is deductions like that. So this plays an important role. So this is the cosine similarity, it is inverse functions this is taken. That is the computes the correlation between the groups, right? So combine two groups. So when we are going for this, this can be based on the metric. This can be a minimizing function or maximizing function. Okay, cosine values, cosine similarity can be maximum of 1, minimum of -1, -1 to 1. This can be like that. Okay, so when we are having this 1 minus in the sense that it will be getting 0, or we can say that can be from 2 positive values. This will be getting maybe. So combine two groups for which D is minimum and change R is equal to R minus 1. That means the number of groups we can keep on doing this, right? But this is for hierarchical clustering is large group. among the large group first we have to do. Then based on the groups, then again for this group same, again for this group same process we have to. Okay. So now this W correlation is nothing but weight correlation. Now using normal correlation, now we are going for weight. Weight correlation means we are giving some priority by applying some weight so that it can be the computations or this can be reduced, and also we can go for a particular localized output segmentations properly. Okay, so this WN, this we can say W correlation minimum of, that is number of object groups, we are saying it is L, and we are saying that we'll be having the data, that means this much data. Based on that also we can have this W. These are all, it's not a hard and fast stringent rules. People have applied this and they have found out the correlation, right? This is the inner product norm of that value. Instead of D correlation, they are using normal correlation, they have used W correlation, and they have found out that whether this particular pixels belongs to the particular group. That is the important thing that we have to. Okay. Then instead of k-means, now we had the famous algorithm, that is fuzzy c-means. Okay. In fuzzy c-means, what? Fuzzy clustering, the data point can belong to more than one cluster. This is the question earlier it was asked, if the same distance metric is there, right? In which each data point can belong to more than one cluster. There may be possibility. But this can be avoided, or this can be this by going for a minimization of the objective function. So here we are just fixing an objective function. This is the Euclidean distance with the weight. C is the number of clusters. M is the fuzzy coefficient. Always we are saying this M greater than 1. N is the total number of vectors. Okay. So now you know fuzzy logic. Fuzzy logic will be having, each and fuzzy logic will be having a membership function. We have to convert that particular information into a membership function. So now see that update the membership for input object with respect to jth cluster is given by the with this function it is given. But this is not a stringent thing. We can change this. Then update the cluster centers, right? Every time the cluster centers are updated with calculated value, this WH. So fussification is done here using the membership function. That is very much important. Fussification. So every time a cluster we have to define number of clusters, right? Then we are saying distance metrics, right? Then fussification is done using this function, right? Cluster center, earlier we have used for k-means mean value. In Medoid's algorithm, we have used the same value of the object. Now the update of the cluster center is based on the membership function fussified value with a normalized value, right? So we are saying that we'll be having here a cluster center. Once the cluster center is updated, again same procedure, right? So fuzzy c-means is same as k-means when M is equal to 1. So this is M when the fuzzy coefficient is M is equal to 1, then it is same. But if it is greater than 1, then we are saying it is fussification. All the weights will be equal when M tends to infinity. So this fussification we know, once we have fussified, then we require an extra function for fuzzy logic, fuzzy c-means algorithm, for that is the defussification to get the exact value, right? So defussification, the process of producing a quantified result. The simplest defussification method is choose the one with highest membership. So here we have made the membership function. Then we have assigned defussification is simply the direct representation. The object is assigned to the group with highest membership. So this is defussification. This is one of my student who has done to show you, to get a thought of that how we can modify the methods, right? Modify the algorithms or like that. Just I have to. Now you see he has made a very small change in the correlation. In the proposed algorithm, the norm x minus y, this is the norm, L2 norm, is replaced with an inverse of correlation. So he has now replaced with the inverse of correlation. Inverse of correlation, whatever values there will be having higher, here we have to consider as lower. So here he has used this fuzzy c-means, this algorithm, okay. Where is that? This. Suppose if I'm saying that this is the cosine similarity function, okay, and here we are having this, okay, objective function. So proposed algorithm, the norm, this norm function, wherever we are using that norm is replaced with this. So that is inverse of correlation. So correlation is unit independent, that is correlation of xy and x to y is same, but Euclidean distance is different. So by replacing this by an inverse of correlation, what he has observed is that, right, correlation is unit independent. Unit means scaling. Now you see that x, y, then we can say that it is x to y. Those things, when we are just considering, all correlation is same. But for this, we are saying that there is a difference. Euclidean distance is different. So for example, correlation of two sinusoid signals with frequency difference 1 Hertz is nearer to 0. So inverse of correlation will be higher. This is the point he has mentioned. He has made it. What do you mean by this? Correlation of two sinusoid signal with frequency difference 1 Hertz. For example, by changing this metric to inverse, I am having a signal, 100 Hertz, 101 Hertz. I am having these two signals are merged together. Small change. I want to segment these two. This is one of the application for ECG. Okay, there will be a very small frequency difference. Now earlier, what is the metric or what is the norm used here is that this norm. This norm is used. When using this norm, using fuzzy C means when we are just segmenting, it is showing only one peak as segment. Because these two frequencies are shown as only one, it can't able to separate it. That's why correlation of two sinusoidal signals with frequency difference 1 Hertz is nearer to 0, right? So inverse of correlation will be very high. So now if it is nearer to 0, then when we are taking inverse of correlation will be very high. So now when we are going for this method, it is showing 0, so there is no clusters. But when we are going for inverse, then the small change also it is shown separately. So it can cluster or it can separate these two frequencies easily. So norm of these two signals will be small. So the signals will belong to the same group if norm is used. Instead of norm, if the inverse is used, inverse value is different. So this will be easily separated. So the metric, you see that how important is the metric? It is also based on the problem. So in ECG signals, noise is a very important thing. 100 Hertz and 101 or 100.05, those things we have to separate it out because ECG signals will have very low frequencies, right? Less than 50 Hertz or like that. Suppose here it is 100 Hertz, I am saying. If it is 35 Hertz, 35.1 Hertz, if I want to separate two peaks, it would have. If I'm going for the normal fuzzy, it shouldn't able to segment it. But if I am just changing the metrics to the inverse of correlation, then it can able to show two separate peaks easily. So this is the finding he has obtained by changing the metric. So now see the fuzzy C means same flow. Instead of this norm function, he has used the inverse correlation function, right? So these output also, it has given a clear output for this context. So this is the thing that we have to work out to get good algorithms for clustering or segmentation or for any, we can say that this is one type of falsification, right? The falsification method, it is followed is norm. We can follow any type of metric or mathematics to overcome certain things. Just your thinking is required. Just to show you an example, that's why I have just one more method. So somewhat it is fully theory. It is very difficult to listen also. But once you have got some idea, if you go and read, it will be helpful for you to get something. That is the thing. You don't want to fully understand what I am telling, but some basic knowledge if you get, and if you go and read the papers or text, then it will be very good. Okay. So this is the last thing I am just going to focus. mean shift clustering. Another type of clustering algorithms is also partitioning based. Okay. So this is now we can say that it is a type of statistical methods using modes. Okay, modes. Now you see that this is a histogram of a particular data. Now we want to find how many modes are there. Modes means we know that the occurrence of a particular event, how many times it has occurred. Based on that, we'll be getting the some details. We can separate it, right? This much numbers which we have, this means then we can separate it like this. So how many modes are there? Easy to see, but hard to compute because one by one we have to see those things. Suppose if I'm saying 2, 3, 2, 2, 2, 4, 5. What is the mode? We can say that mode is 2. Right? How many times it has occurred? That may be possibly the mode can be more also. Many number of data occurrence, more frequencies. How many times it has occurred? Based on that, we are saying this is mode. So now finding modes in a histogram. So here it is window based. We are just fixing one window. In that particular window, we are just finding the mode. Based on that mode, we will be having a mean. With respect to that mean, we are shifting the window. Like that, we are just going on shifting the window and we'll be finding the best optimal value for clustering. Mean value, we can say. So initially it's the random seed and window. Okay, first we'll be just finding a particular window. Calculate center of gravity of that particular window. That means center, right? So translate the search window to the mean. So with respect to the mean, we have to translate the particular search window. So we are saying this. So this is repeat step until we will be getting the convergence. Again, if we do shifting means we have to shift it. What it means, that means we'll be having clusters. Initially, we'll be having the center here. Then based on the window shifting, the cluster may be going here, right? This will shift here, right? Then it will be shift, it can shift here. At last, once it converges, then it will be coming to the exact center. Like that. That is the matching. So we are saying mean shift approach. This window is required, sliding window is required. Every time we'll be finding the mode. Then based on the around the mean, we are just shifting. Here, this is, even though I'm explaining like that, this all depends on the density function distribution. That I have not brought out here. This is the density function. Okay, we will be making a Gaussian distribution around each point, like that. So initialize a window around each point. See where it shifts. Okay, it can shift to right, it can shift to low. We'll be calling it as a mountain hill problem. It can go to the minimum maximum value, moving towards that. Downhill problem means this. Right? So first run the mean shift procedure for each data point and store its convergence. So now convergence point means we'll be having the data here, whichever data which is having the relevant things, that we are calling it as the convergence point, right? So link together all these sets that are closer from each other to form clusters. So this is the first thing. First run the mean shift procedure for each data point X and store its convergence point Z. Then we have to link all the Z's which has converged to form a cluster. Right? Assign each point to its cluster. If the cluster is very small, then we can eliminate the regions. Otherwise, we can preserve it. So all this is one type of statistical, and we can say that heuristical, but it is a window-based method. So convergence is also somewhat how we are moving the window, how it is get converged. It is all based on same as that of, we can say, the k-means, right? Because it is mean shifting, right? Every time we'll be calculating around the window the mean, and with respect to the mean, we are finding the distance and the convergence. And if it is less than that means, we'll be just making clusters around that. Then again, we are finding the mean, and towards the mean, we are shifting the window. Then again, in that window, whether we'll be having the convergence again. If it falls on that, then we'll be moving the data into the particular clusters. Like that, we are going for segmentation. So mean shift for image segmentation useful to take into account spatial information. Instead of RGB, a mean shift algorithms used RGB XY space also. That means the particular positions, coordinates also it has taken, many algorithms has come. So this mean shift, it is in the MATLAB, I think so. Mean shift algorithms, clustering based, that you can see that how it is working. Number of windows, slidings that it has to go through, the iterations, number of iterations, those things we have to give. So based on the data, it will be converging. So one thing is that now you see, guaranteed to converge to a fixed number of clusters. The mean shift clustering is giving a guarantee that it will surely enter into the fixed number of clusters, because we are going for taking window, okay, and we are from that window, we are just analyzing, taking the mean. Towards the mean, we are shifting our cluster center. Then from the cluster center, again, we are finding the values. Like that, it's keep on going. So it's purely a statistical method, because based on the mode or operations, we are just finding it. Okay, so this is one type of method. And nowadays, people are working on clustering with the ANNs. So that is that I have not taken. Just I have given the basics of different types of clustering. So these are things I have planned to focus to you. I'll come to the first slide now. So now you see partitioning based methods, fuzzy. Okay, fuzzy C means only objective function and membership is different, right? K means K methods. DBC method, that means larger group, smaller groups. Agglomerative methods, from smaller groups, we'll be finding larger groups, right? These are hierarchical methods, but tedious task computation wise, but as somehow maybe enter with good outputs if we have the patience and the resources to compute and all those things. Okay. Then I have told about the density based methods, right? So one of the density based methods is that the last what we have discussed, the mean shift algorithm is density based. Mean shift. Okay, probability distribution. Then we have also from the k-means we have tuned to some EM algorithms. Using EMs, how we have made into clustering. Problem formulation is important. We'll be just having continuous function distributions. The data we are matching to a continuous function. From that we are defining mu variance. Clusters also different clusters we are defining. From that clusters we'll be finding the expectations and maximization. So EM. So AN clustering is also there. Nowadays lot of algorithms has come, right, for AN clustering. Then graph-based, the simplest graph-based algorithms, right, using based on the weight matrix, similarity clustering, eigenvalue problem, formulations like that we have seen. Okay. So these are the different methods, basic methods in which we are having clustering. So based on the nature of the applications, we can select any methods in and around that, and we can give modifications on the objective functions metrics, and we can see that how the results are like. So with that, my session, whatever I have planned to present is getting over. So thank you. Any questions on the side? You read it, then you will be getting some more idea, because the most of the things are mathematics. So I'm not sure what you have got. Okay. But if you have some tutorials, you just explore that and see, then you will get able to understand. Tutorial in the sense that I'm telling about the numerical values calculations, like the take a 3x3 matrix or a 10x10 matrix, do the calculations on your own. Then you'll be getting a good perspective on that. Then you will be getting more ideas that how to change it. Okay. Thank you.
Thank you, ma'am. Thank you very much. It was really very informative, and you have discussed nook and corner of the clustering techniques, and you have also detailed on the k-means clustering. I hope participants will look forward for further tutorials as you stated, and they will try to get their expertise on this. Madam, thank you very much. And you have also concluded at the right time. Ma'am, if you see in the chat window, of course, some questions have been posted. If you can answer those questions, it will be really grateful, madam. For 5 minutes, will it be okay with you, ma'am, for 5 minutes? Or you want me to read the questions, madam? Many questions you have answered also. Madam, am I audible? Shiva, madam,
Yes,
am I
you
audible?
are audible. You are audible. Yes, now I can see.
Yeah. So,
I
ma'am,
can value.
I'm just scrolling through the thing, scrolling through the chat window. But I think most of the questions you have answered, ma'am. Like, you know, the fast participants have also posted some of their answers. So I'll read the question. How to measure accuracy in a cluster is the first question, madam. Okay, madam, I think there is some connectivity issue. What I will do is I will mail the queries to you, and then I will get the answers and I will give back to the participants again. Thank you very much, ma'am. Thank you for your, I know you were amidst of the busy schedule, and you made it as a point to join us and support our participants. Thank you very much, madam. Thank you. Participants, can you hear me?
Yes, ma'am. Yes, ma'am.
Yeah. So as per our schedule, 11:45 to 12, we will have a short break, and we will stay tuned in. Like, you know, we will start the session exactly by 12 o'clock again for the hands-on session. Hands-on session will be again conducted by Dr. KG Suma on the segmentation techniques. So let us join back by 12 o'clock. Please try to be on time so that we can continue with the sessions. Thank you. Do not disconnect. Just go take a break and come back.
Ma'am, when you will share the PPTs?
Sir, PPTs have been yesterday's all PPTs have been uploaded in the Atal portal. So if you have gone through the link, you can download from there. Yesterday itself, we have uploaded all the PPTs.
Please provide the link.
If you have any concerns, like, you know, if you are not able to, because
Ma'am, your voice is not clear.
now, is it not clear?
No, I think from my side, ma'am, your voice is not clear.
Yeah, it is yes, clear, madam. Your voice is clear, madam. But if possible, please provide the link of that particular Atal link. Okay.
Okay, sure, sir. If still there is a problem in accessing because yesterday evening itself we posted, that is, we uploaded all the presentations. If you are not able to access, then I can directly, send it to you. You know, we have the WhatsApp group, right? In the WhatsApp group, I can send the presentations to you so that you can have a look at it. Is that okay? Just let me know whether you are able to access or not. If you're not able to access, then I will provide you. And now I'm posting the link for the session, the day 1, session 1. Okay. So you can
excuse me, ma'am.
1 minute, sir. I'm just posting the link. Okay, so you can find here day 2, session 1 link. The first 15 minutes was only like based on the feedback. We have given that's a short session for the medical image resources. So the actual session is the day 2, session 1 is what Dr. Shiba Rani has presented. So you are giving feedback for Dr. Shiba Rani. Yes, someone asked me a question. Yes, please.
Ma'am, yesterday you put the assessment link after after 8 o'clock. So if it is like it is better if we will have in continuation.
No, actually, I have posted it for the faculty members or the participants who have not taken it. So it is only an additional. Otherwise, then and there we are giving the what is that assessment link. Today, like in the part in the feedback, faculty members, I mean the participants have stated that it is better to have the assessment at the end of the day. So what I will do is by today by 4 o'clock, I will post it. But some of them are in travel. That's what they are telling me. Some of them, they are saying that we are in travel by 4 o'clock. So it is not possible for us. So what I can do is unanimously on by 6 p.m. I will put 6 to 6:30 p.m. Try to complete the assessment alone. Feedback will be given then and there as and when the session is over. Am I clear?
Yes, means like we can submit the test from 4 to 6, anytime
Yeah.
between 4 to 6.
2 hours
Because
will be too much, sir. We cannot give 2 hours. That is the reason I will post by 6 o'clock. By 6:30, you can
but
submit it.
ma'am, for us we actually travel at 6 o'clock. That is the problem.
Okay. Then I'll do one thing for all of them. I'll post by 7 o'clock then. Because for each person, if I try to cater, it will be not correct. So 7 o'clock, I will post 7 to 7:30. You try to submit it.
But I think probably like at just at the end of the session, if you
No,
give
at the
the
end of the session, what happens is some are saying yes. See, we cannot satisfy all the participants. It is very difficult, right?
Madam, but what I was saying that please, at whatever time you say that you will post the quiz, please post at the same time because we are continuously waiting. And yesterday it was very difficult to manage at home also.
Yes, madam. Yes, the same experience here also.
No,
So it will be nice if you post it after
from
immediately
our
after
side
completion of
also
this
we
session.
had concerns.
Okay.
From our side also, yesterday, we were here till 7:30 in the on other tasks. We also had the parallelly other tasks. That was the reason. So today there won't be any such thing. The time. So what I will do is, so unanimously we agree that 7 o'clock I will post. 7 to 7:30 you can complete it. For sure it will be posted in the time stated. Fine.
Yes, ma'am. Thank you so much.
Thank you. Thank you.
Okay. Good afternoon, all. Let us start with day 2, session 2. This is actually session 6 as per the schedule. 12 to 1, hands-on session on the segmentation techniques. Dr. K.G. Suma, Associate Professor and Placement Coordinator, KL University, will be hosting this session, the hands-on session, in image segmentation as well as thresholding. So, Madam, I'm handing over the forum to you. Kindly proceed.
Yes, ma'am. Thank you, ma'am. Dear participants, I'll forward the coding to you in your WhatsApp group. Okay, from there you can retry and open the Google Colabs. Google Colabs.
Participants, can any one of you download the WhatsApp? I have sent the file in the WhatsApp. Can you please tell me whether you have received image threshold? Uh, am I audible?
Yes, ma'am, you are audible. Yes, ma'am, you are audible.
Okay. So did you receive, sir, the files which I have
Yeah,
shared in
yes,
the WhatsApp?
exactly, ma'am. Yes, ma'am.
Did you receive image thresholding file?
Yes, ma'am, I got both the two files and I am right now downloading.
Uh,
Ma'am, we have to check. It is just downloaded, so we have to check.
yeah, please check, sir. Please check.
Ma'am, through Colab itself, we have to execute it.
Yes, please. Can you open that link?
Provide the image files also.
Able to open that link?
The INB files are opened, but the image files will also require. We don't have these image files.
Yeah, we are getting it, ma'am. The threshold exercise that
Yes. Okay.
that 97.
You got
that is working. That is working. And I have to check the 98 last.
So you received the image thresholding file, no, sir?
Yes, yes.
Yes, yes. So I'll forward image segmentation as well as k-means clustering also. Okay, 1 minute.
Okay, ma'am. Ma'am, we can execute this from Jupyter also, no?
Yes, sir, we can do.
There is no problem. We can. Okay,
no.
thank you. Okay, thank you. Yeah, this morphology one also received 98. The last number, last two digits are 98. Here we have median filter, then corrected, noise inserted.
And for the drive, please give the access.
Excuse me, am I audible to you? Hello?
Yes, sir.
Madam, please provide the image source files also.
Yes, yes, I'm sending, sir, actually. That's what,
Right?
in WhatsApp, can you able to see the files or not, sir?
We are able to access the INB files, but not the actual image files.
Image also I'll send.
Okay, thank you.
Image is there along with it, so not a problem.
Image file is sent to your WhatsApp. Please try to take all the files into or just take 5 minutes time and try to get everything.
Please answer to the questions posted in the chat box.
Who is hello?
Madam, we are unable to access the link provided in the chat box here in the WebEx.
Sir, I understand. Please hold for some time, sir.
Acha,
Please.
okay. Okay, thank you.
We are the cases here, right? So please hold. And like we are if we are trying to give individual access, each individual is asking for the drive, so it will be time consuming. So we are planning to send it through the mail.
Thank
Fine,
you so
sir?
much. Thank you. Mail is the best option. Thank you. Okay, thank you.
Yes, good afternoon, participants. So, the process of sharing the folder is in work actually. So, ma'am is forwarding the files. Okay, so I'll start the presentation anyway. option. Okay. Can you see my screen?
Yes, ma'am.
Yes.
Yes, ma'am.
Audible? Yes. Can you see my screen, please?
Yes, ma'am, it is visible.
Yes. Okay, okay. Yeah. So in this session, we are going to see about various segmentation techniques and then implementation for the same. Okay. So the files are in process. So once you reach, I'll start explaining, means I'll start the hands-on session as well. So image segmentation, our ultimate aim is we have to segment the image based on the region of interest. That is your interest, that is which region that you want for your further processing, that you want to make it segment. Or else what will happen, the process will take more time and the needed, that is which region that you required will not take for the further classification work or deduction work. So to make it simple, what we will do, we will extract the region of interest.
Okay, sorry to interrupt. Participants, I have forwarded all the required files, the Python files as well as for the hand session to your mail. So please download the files and you can utilize it. Thank you.
Okay. So in segmentation, we have to find the region of interest, which region that we required for further processing, like classification or object detection. So for example, if this is the image, what we will do, we will segment in an appropriate regions. Okay. So if I need mountain, I'll separate according to that. Or if I need this water, I will separate. Or if I need the land, that I will separate. So this is my ultimate goal. So once after I separate, I'll find the features from this, which leads for classification purpose. Okay, so the total image, if you are doing the feature extraction and everything, it will take time and appropriate accuracy for your region of work may not happen. So what we will do, we will extract that which we require for the further process. For example, if it is in child surveillance, what we will do, the child movement alone we have to identify, right? So the background and all we will not consider. The child movement alone we will consider. So the child is a region of interest for you right now. So likewise, every application we have to go based on the region of interest. So we'll start with the techniques as well as the implementation. So first, morphological segmentation. This is one common segmentation which helps to identify the region very easily, and we can separate it very easy way. Okay, just converting the regions into black and white color. Okay, so that is morphological image processing. So this consists of two different operations. So participants, you don't again access is required. Can you able to open the files, ma'am? Anyone please say to, from the mail, can you able to open?
Yes, ma'am. All the files are downloaded and we have placed in the drive, ma'am.
Okay, ma'am.
Yes,
Okay, thank you.
it can be
Thank you.
opened
Thank you.
from
Yes.
the mail. Thank you.
Yeah. So if this is the image, that is the first is a image in the sense, then what we will do, we are converting generally from the grayscale. We will convert into the morphological segmentation. Okay, this is a very basic thing. So we are converting the image that is from the grayscale, we will convert into black and white. Okay, so that by having some threshold value, by fixing a threshold value. So for example, if 150 is a threshold value or 150 pixel value is a threshold value, we will fix in such a way, or 50, whatever may be the point. Okay, we have to find out from the pixel, and then based on that we will do the threshold. This is common threshold. So from that we can do dilation process or erosion process. So dilation in the sense, for example, if any disturbance in the edges are there, what we will do, we will dilate. Once again, one more point we will add, and we will make the edge into very clear. Okay. See, for example, if this is a picture, if we are adding one more point to the next the next pixel, what will happen? The edge may be little clear. So that one can be done. Okay, this is called as dilation operation. When you do erode, that is erosion operation, what will happen? It will again thin. Image will get into thin. Image thinning can be done. So depends on the application. Say for example, image thinning, we will use generally in fingerprint related images and all. If we do image thinning, thin lines of fingerprint that we will get, which helps for pattern recognition easily. So likewise, if it is dilation in the sense, if the edges are not at all clear, very very disconnected here and there, then what we will do when we do the dilation, it will try to connect the edges between one point to the another. So based on the need that we will do. Okay. So now we will go for our implementation work as well. So what you do, I'll start with step by step. First, you open Google Colab. So open it. So before that, you go to your drive. Okay, that is which mail ID that you are using. So go to your drive. Okay, Google Drive. Right. So you can create one folder. Okay, so create one folder. In that, you paste your images. Whatever I forwarded, you paste the images in that. Copy, download it and paste it. Okay, then you go to Google Colab. Once you paste it, go to the Google Colab. So as soon as you go to the link in Google Colab, you will get this type of window. In this, upload. Okay, so you choose a file. Already 3 files were shared, no? So you choose image thresholding. Open. Right. So you'll get all the codings what I forwarded. So what you do connect in order to allocate the space. Yeah. Once after it connected, it will show the space actually. Okay, till that you have to wait. Then you go to this files. Okay, we are going to access our file, our image file. So go to files. Okay. Then click to this drive file, mount drive. We have to mount our Google Drive. Okay, we copied our images over there, no? So you have to mount your drive. So click that. As soon as you click in the coding, it will show to run this code to mount the Google Drive. Okay, run this cell to mount your Google Drive. So just run this first. Okay. So you will get this type of message actually in order to connect. So connect the Google Drive. Okay. So after you will get this window. So in that where you saved that Google Drive, right? So that account you have to click and then go to allow. Okay, now the drive is getting import actually. Right. So you will get tick mark and the message will be like mounted at some path, that is your drive. Okay. So next Once the drive mounted, just refresh the folder once again. Here, this refresh. Okay. As soon as you refresh this drive, that is your drive actually, this is. So you click this folder and then in that my drive will be there. You have to click that.
Yes, madam.
Okay. Within that one more folder you have created. No, I have created FDP images.
Oh, I'm sorry.
So you can what if your image is straight away in the my drive, you have to find out. Okay, in this list you will get it. You have to search that. But I created one folder. So you click that. All my images, whatever I have imported in that Google Drive, will be displayed here. Okay. So now I'm taking mountain PNG. Actually, PNG file I'm going to use. As I told yesterday itself, no JPEG, please don't prefer. So PNG you can take. So click the PNG file, that is mountain, and then copy the path. Okay, copy path. Then in this IM read, okay, we are changing the path actually based on our image. So copy the path. Now the path was copied. That is mountain 1.png under FDP images in my drive. So it's copied. Now I'm going to run this. Yeah, sorry. Before that, the file should be imported, no? So the first segment, okay, you have to import actually. So first run that, then you come here. Okay, import that first segment. Already the drive was mounted. And then as soon as you copy the picture path, you run this. Now, yeah, now you're getting the binary, that is morphological thresholding. Okay, so up to this. So various morphological processed images displaying here. Okay, binary inversion. These are several functions actually. Okay, which includes dilation and erosion concepts. Okay, 2-0 inversion, 2-0 truncation, binary inversion, image thinning will be there. What is it? Image erosion will be there, image dilation will be there. So you will get several number of different region based segmentation. This is simple morphological segmentation. Okay. So this is the work. So this is for morphological segmentation. Yeah. So if it's done, we'll go for the next session. Shall I wait or wait? Okay. Yeah, dear participants, if you completed this concept, if anyone share the screen, I'll make it. I'll get confirmation. Then we will go for the next work. So I'll repeat. See, first you have to open the Google Colab. Next, you do connect here in this right side. Connect will be there. You have to connect. Once after you get connect, go and refresh this file. Okay. What happened? Oh, ma'am is sharing. Someone is sharing. Yeah. Yes, ma'am. Just go up. Yes. Thank you. Thank you, ma'am, for your confirmation. Thank you. Thank you. Yes, ma'am. Thank you. Thank you for this confirmation, ma'am. Yeah. Thank you, ma'am. Thank you, Shirley, ma'am. Thank you. Yes, yes. So we'll move for the next topic. So I'll give you 2 minutes of time for everyone to implement it. Please. Yes. I'll recap once again how to upload that. So first you have to copy the file in your Google Drive. Okay, create one folder. For your research work also, you have to do in such a way only. You have to create one folder and copy your files. Okay. And then go to Google Colab, right? You have to connect this. Once the memory is getting allocated, then you have to import your drive, because in drive only you are having all the images. So you have to import your drive. So first you mount the drive. You have to run this. Okay. Once it imported, then you will find your drive in the left side. Okay. Consequently. Okay. This drive, and then refresh the drive. From the drive will be there. In that my drive will be there. Within that, any folder if you have created, it will be shown. That's it. So you copy that path by click this settings. You can copy the path and you copy the IM3. Yes, that's it. So that this code will be executed. This is common threshold. Okay, I'll tell you how to find the accuracy in this thresholding also. Okay, definitely I'll tell you. Thank you. I'm sorry. Sorry, sir. Wait, I'll repeat. Yeah. So you have started with global thresholding. This works. Repeating. Yeah, I'm repeating once again. Yeah. So this global thresholding, it works well in situation where there is clear value. Okay, clear value is nothing but clear condition of image like fingerprint, iris. Okay, that and all will have some pattern, no pattern like combination. That is, it has a very clear value. So those type of images can work very good through the global thresholding. Okay, so next, adaptive thresholding. So what it will do in the sense, it works good in the lighting conditions based image. For example, in the illumination disturbance or any shadows disturbed. Okay, based on that, we will get some blurred image. No? So in that, if you are using adaptive thresholding, you will get good results. Okay, if the image is blur, like surveillance image or anything, you can use this adaptive thresholding in a very good. So this has two common methods. Adaptive mean thresholding, adaptive Gaussian thresholding. Okay.
Expected time of expected time of
Am I audible or not, please?
loss means entropy. Entropy.
I'm speaking.
Yes, ma'am, you're
Entropy.
audible.
We can call it.
Yes, thank you. Okay. So these are the two types, common types: adaptive mean thresholding, adaptive Gaussian thresholding. Here, how the threshold value will be identified in the sense, the threshold value is the mean of the neighborhood area. Okay, that is, if you take 3 cross 3 pixel, mean will be taken, and that one will be considered as a threshold value, right? Same way, adaptive Gaussian thresholding. Okay, weight, the threshold value is the weighted sum of neighborhood values, right? So some weight will be declared for that, and based on that, we will collect the neighborhood values, and we will do this type of work. So adaptive thresholding, which works very good in lighting conditions, blurred image. So you can utilize these two thresholding, mean thresholding and Gaussian thresholding as well. Okay, so like this. See, for example, this might be the example for the source of the image. Very illuminated. It's not crisp and clear image almost. So we used to get like this in a surveillance camera mostly, right? So this type of image will have various shading here and there. So by having the thresholding concept, we can able to detect that, and we can find the, if you know, if your region of interest is not matching with the what shaded portion, you can remove also. See here inside the same condition is there. If it not required, we can remove that. All right. So we'll go for the execution now. Yeah, this is the difference. If you see, this is the difference. So this, if this is the original image, how the global thresholding is there, you just see. It's just a thresholding. Okay. This is it doesn't means we can't adjust the illumination or anything. Whichever the clear portion is there, that will be displayed very good. So that is the thing. And adaptive mean thresholding, this is a work. And adaptive Gaussian thresholding will get little very good clear. Okay, so now we will go for the implementation. So same code only. If you come down, okay, you read the same image once again. Same mountain image. Copy the path. And then, yeah, okay. Same mountain image you copy and then you just implement. Yes. So the output is here. Okay, as I explained, the global thresholding is very, based on the threshold value, what we are identifying, we are just doing. And then adaptive mean thresholding, this is the output, and Gaussian thresholding, this is the output. And the picture is very clumsy here. So here we are getting the thresholding also, we are seeing it's not much clear. But for your application, you can get it. See, in this adaptive mean thresholding, the very disturbed pixels are segmented, if you see. But when we go for the Gaussian, unwanted and all might be eliminated. Okay, as like what I displayed here. See, here you can see many dots, but when you come here, that noise also might be removed. Okay, and then in Gaussian thresholding, you can see very clear. So all of you please implement that also. So global thresholding, mean thresholding, Gaussian threshold. Okay. So same file, again you copy in the IM read and execute it. You can see the pictures. Okay. So I'll give you again 3 minutes. So implement it and show me in your screen for a confirmation. Yes, ma'am. Yes, yes. Yes, ma'am. Thank you. Thank you for your confirmation. Yes, yes. Ma'am, we will start the next execution within 2 minutes. Thank you, ma'am. Thank you. Thank you. I can see your screen. Thank you. Thank you, ma'am. Thank you. Thank you for your confirmation. Ritu Rana. Thank you. Thank you, participant. Okay, so again we will start the method. Okay, next is Otsu method. This is also one novel thresholding technique. Okay, so this includes much more steps actually. Okay, so it works from the histogram onwards, and it will collect the threshold value from that, like maximum intensity value it will take, and then it will work for the thresholding value. So I'll explain that. So also threshold method involves iterating through all possible threshold values and collecting a measure of spread for the pixel value each side of the threshold. So what it will do in the sense, it will compute the histogram and it will collect the probabilities present in intensity values. Okay. And it will find the maximum intensity values. It will collect two maximum intensity values. Okay. Greater and equal maximum. Likewise, it will collect two intensity values. Based on that, the threshold will happen. So this is a novel method which was derived by research people, and it is in form now. And many applications, they are using this Otsu method for the thresholding purpose. So likewise, novel method is also there. Several novel methods are there. If it suits for your application, you can utilize. Okay, you can identify the accuracy. I'll explain you how to identify the accuracy also for the segmentation process. So now we will implement the Otsu method. Same way, you come down. In that, again, the coding is there. You copy the path, the same path. Copy the same path, and you can see the, yeah, run it. This code, which includes all the work what I said, and you will get, see, the histogram also will be shown actually. So based on that, you can see the Otsu thresholding works. Okay, so in my code, what I was trying to do in the sense, original noisy image will be there. So from that, I have done some Gaussian filtering also. Okay, in order to make it very clear, that is edge. So I have done the Gaussian filtered image, and then thresholding we have. Okay. So whatever the pre-processing that you are doing, you can do, and you can proceed with the also threshold. Not only this, all the thresholding, before that you do some pre-processing work, equalization or whatever it is. You can do it, and then you can proceed for the thresholding. It may be global thresholding or any other previous work like Gaussian thresholding, mean thresholding, okay, adaptive thresholding, sorry. So, and then Ozu thresholding also you can. So next, we'll go to edge detection. Okay. So all of you might know this canny edge detection, right? So you see the difference. This is Sobel actually. Okay. So there are several edge detection methods. In that canny edge detection, which plays a vital role in many applications. Okay. So there are commonly Roberts edge detection is there, Purvitt edge detection is there, Sobel edge detection, and then canny edge detection. Okay. Depends on the application, you have to choose. Okay. So this is Sobel actually. The top image is Sobel and this is canny. You see the connection, no? The detection, the, what is it? Borders, the contours is very clear when you see the canny edge detection. This is also having its own novel procedure. Okay. Gaussian convolution. Then it will find the intensity gradients of the image and it will thin the edge. Okay. Like image erosion. It will do the edge thinning and then it will apply the double threshold value. Then you will get this form of image. Okay. So it is the inner work of canny edge detection. This is a common 4 method: smoothing, finding gradients, non-maximum suppression, hysteresis, thresholding. So it includes all the steps. Okay. So we have to learn the steps also. So here, how it is identifying the intensity gradients in the sense. See, the image will consist of the edges, right? So it will detect how to identify the edges, like whether it should move to horizontal or vertical or diagonal, how it should compile the image, how it should mark the image will be identified in this process. Find the intensity gradients. For example, if you come here in this point, whether it should go, it should connect top to bottom or vertical or diagonal. Okay, that will be understood in this detector and it will act accordingly. Okay, the connection will be automatically done. So just implement the same code. You come down. No, it's not same code. You go for image thresholding over it. Next file, image segmentation. So close this collab. Open again. So Google collab. Right? So open it again. Upload. Choose file. Segmentation techniques. The second file. Segmentation techniques. Open it. Okay. So now you have to connect it. Connect. Okay, it will initialize the memory. Okay. So once after it allocate, you go to the file folder. You have to upload the drive, right? So mount drive. So this is the code for mount drive. So you run that. So connect to Google Drive. Once again, the same procedure how we done it. So you choose your account. Allow. So as soon as you mount the drive, you refresh the folder, go to drive, go to my drive, FDP, that is whatever the folder that you created, and then you take mountain. 1 minute. Let me see. Yeah, take this mountain itself. JPEG. Yeah. Okay, copy the path. So in this IM read, you just paste it. Okay, so run. PLT. Sorry. So the previous segment should be imported first. So first you run that, then you run this. Yeah. Then one by one segment you start run. Okay. One by one you just run the file. This is nothing but flipping actually. Horizontal flip I am doing. You just ignore this. Then once again, next segment. Yeah. 1 minute. There is a canny. So you run all the segments one by one. I'll show you where the canny reduction. It's coming right. Some error. 1 minute. Let's see. Gamma correction, add noise to the image. Sober gray image. Some error. Yeah. Some error actually. Okay. Yeah, 1 minute. I'll remove that. Yeah. So I'll explain on this. Okay. This image that I'll forward to you. Okay, you can work with it. So just horizontal flip, and then this and all is a pre-processing work. So adding noise to the image, this and all is pre-processing work. See here, this is a Sobel edge reduction. Okay, how you are getting after applying the noise. Okay, and this is vertical Sobel, horizontal Sobel, and then if you see the canny edge reduction. Okay, so you can see the connected lines very clearly. So Sobel filter in the Sobel edge reduction was considered like a filter here. And then if you're proceeding the canny edge reductor for that, it will show the closed regions clearly. Okay, I'll share the image once the session done. I'll share this image to you. Okay, so next, as the k-means clustering, See, morning session was detailedly covered this K-means clustering, actually about the K-means clustering. So I'll show you what is important in this K-means clustering, right? So if you see the this image, okay, this vegetable image, based on the color, we can able to separate the cluster. See here, I made 3 clusters, right? So when I do that, the red based cluster, which is in one plane, and then green based cluster, which is in one plane, and the beetroot color cluster, which is in one plane. Okay, if you increase the planes, if you increase the iteration, like more than 3 cluster, like 5 or 6, what will happen? Even this red will separate into 2. Okay, even this green will separate into 2. It based on the intensity variations. So here I made 3 clusters, so 3 different images it is shown. Okay, so how to identify the accuracy? See, actually, after doing the segmentation process, you are having the truth value. Okay, you have to develop the truth value by having image annotation work, or else the truth value will be presented in the online datasets itself. Okay, so you have to collect true positive, false positive, true negative, false negative values. Okay, I repeat, true positive, false positive, true negative, false negative. Okay, see, for example, this is any application which has healthy environment. Okay, and your identification also healthy from the ground truth value, then it is true positive. Okay, you have segmented into a healthy, and in truth value also it is healthy, then it is true positive.
Excuse me, ma'am.
Okay,
Is it like a confusion matrix? Is it like confusion
sir,
matrix which we are calculating?
it's
Is it
not.
like confusion matrix we are calculating? No, true positive, false positive, true negative, false
Yes,
negative,
sir.
like that.
Yes. Okay.
Okay, ma'am. Thank you.
So we can compare with our truth value, sir. Our deduction, our separation is there, no, in segmentation. So from that, the truth value we have to compare, right? So that we have to identify in such a way. And false positive value, how it says in the sense, healthy, if it is healthy, what you segmented, it's healthy. But in truth value, ground truth value, if it is not healthy, not healthy in the ground truth, that is original is not, but your deduction is like healthy, then it is false positive. Okay, this is common for all the segmentation accuracy identification. Next, true negative, whatever you have segmented is unhealthy, and then the ground truth value is also unhealthy, then true negative. Okay, both are unhealthy. You have deducted correctly, and the ground truth also unhealthy, then it's true negative. If you go for false negative, you have separated as unhealthy, but the ground truth is healthy. This is very wrong. We should get very less false negative value when you go for the accuracy identification. Okay, so this false negative should be very, very less value. When you do the work, this false negative should be very, very less value. Or else the accuracy you will not achieve the accuracy in a good way. So once after you identified this truth value, true positive, false positive, true negative, false negative, you have to compare, you have to calculate sensitivity, specificity, accuracy. This is a formula for that. Okay, this is a common method to get the accuracy identification. Once you do that, you have to make a column like this with true positive, true negative, false positive, false negative, sensitivity, specificity, accuracy by calculating this. Okay. So this and all will be when you implement true positive, it will identify 2 images that you will give, right? So both the image will be compared and you will get one value. You have to copy that. So likewise, you do that. If you get more accuracy, that is 92 and above accuracy in your research work, then it's success. Like segmentation process is success. You can proceed for the classification work. Okay. This is a method how you are writing the ROC curve also. Okay. ROC curve, which get the combination between false positive rate and true positive rate. Okay, it is a combination between false positive rate and true positive rate. So you can develop that and then you can prove that your curve is good and it is justified. If the curve is not correct, then your accuracy level is very less. So you have to improve that, improve the algorithm or improve the pre-processing work, change the segmentation technique, and you have to implement it. So this is the accuracy identification and segmentation approaches. Okay, so the same thing for k-means clustering also. I have shared the code already. Wait, I'll show you. Close it and I'll show you in that image itself. Just for 2 minutes. So any doubts you can post in chat box. If any doubts you can post in chat box. So allocated memory. Yeah, you just see here. This is the image what I took. Okay, I'll forward this image also. And then see the clusters. So these are the different clusters what we extracted from that image. Okay. So you have to try for, see, what are the difficulties that you will face in image segmentation? This is first thing, threshold level identification. Okay. Second, whatever the code that you are trying, it will show the array out of bound error. Okay. So what you do, you have to resize your image. Okay. That is the first, you have to crop the image into some extent. Mostly you take 512 cross 512 or 700 range. That's it. Not more than the 1000 and all you don't use. Okay, 500 range or 700. That's it. First you resize the image or you crop the image into that extent. Then you do proceed. Okay, most of the code, whatever you are getting, it may not implement because of this purpose only. And then all the image you just convert into grayscale. Then you go for the thresholding work. Okay, or you extract one plane and then you go for the thresholding work. So that the picture will be, the picture can easily take the values for the thresholding work. Or else, if you are doing proceed with the color image, then you will find very difficulty to do the work. So with this, if you have any doubt, you can post in the chat box. I'm here to answer. Okay, then we have
Questions, Adam? Any questions?
no questions.
Okay.
Right. Since we haven't received any questions, so this session, this post session will be on feature extraction processing, and classical neural networks and backpropagation. It will be presented by Mr. Arunjit Chowdhury, CEO of Enterprise Building Training Solution. So that will also be really an interesting session, because the trainer is very experienced person, and he has taught in the multiple. So I expect you all to meet you again by 2 p.m. The session will start at 2 p.m. exactly. You can see the feedback link that has been posted in the chat window for the session. And I could see a few participants, who do not join in the beginning of the session, but I do see them joining at the end of the session. So in WebEx, as you all are aware, we will have the starting as well as the ending time, like, when you are logging in and when you are logging out. Because, see, your continuous presence is very much required to have a proper understanding of the subject. So my concern is all of you will attend regularly. Because 90 or logging in, logging out, again logging in and logging out. So we will be looking into it. And if a session is for 2 hours, a participant who attends minimum 90 minutes will be considered as the participant. Like, and it is have been uploaded in the Atal site, in Atal portal for you to access. In case if you have any concern, please do let us know. We will convert it into PDF files and we can share it in the WhatsApp group. Thank you.
Excuse me, ma'am. Hello, ma'am.
Yes, please.
Hello, ma'am. Actually, I am having some network issues. So in between, I'm getting disconnected sometimes. So I'm again reconnecting. So I'm again reconnecting. So kindly consider that because throughout my sessions, I'm having those problems. Okay, so kindly consider I'm reconnecting back again. Okay.
Okay, okay, sir.
Okay, ma'am. Thank you.
So we will meet by 2 p.m. I'm closing the session for the forenoon.
Into more details, and the second is the linear discriminant analysis. Today's session I'll be focusing more on the PCA because I'll have to also cover ANN, but in PCA I will show you with an example how you reduce the number of features, say from X to maybe 2, and then you calculate the accuracy of the model using, say, confusion matrix in classification model, right? So what I will do here is, this is your data set. Now this data set is a regression model where you have one dependent variable and you have multiple independent variables, right? You have profit, R&D spend, admin, marketing. There are various fields or various features which are part of this data set. And obviously your profit is going to be your dependent variable, and R&D spend, all these are the independent variables, right? Now what I want to do is I will explain to you what is backward elimination. Okay, and then I will probably run this script and show it to you. So imagine that in this scenario, you have profit, and profit depends on your R&D expenses. You have the admin expenses, and you also have the advertising expenses, right? In real life scenario, that could be 50 features or 25, 50 features. I'm just taking a very simple example. Now, obviously, you will run a multi-regression algorithm to find out the model efficiency. Okay, and what is the model efficiency used in a regression model? Anybody can tell me? What is the, how do you measure the efficiency of a multiple regression model? Am I audible to all?
Yes, sir, you're audible.
Am I audible?
You're audible.
Yeah. Okay. So guys, I mean,
yes, sir,
please,
you are audible.
Please participate, because if you don't participate, it becomes becomes very dull. I would like you to guys give some inputs based on your, I'm sure you must be having a lot of knowledge. And I expect that you must be having this basic knowledge about how you measure the efficiency of a multiple regression model. Okay, when you're talking into deep learning, you need to have your basic machine learning concepts clear. So anybody has any idea about how do you measure efficiency of a regression model? So there is something called R square. I don't know whether you have heard about R square. And we also have adjusted R square, typically which works in a multiple regression model, right? Okay. So now what happens is that now this is a bit statistics, and I always
Sir, they are answering in the
their answer is here.
some of them are actually interacting through the chat. Also, and you can proceed,
Okay.
sir.
Yeah. Okay. Mean square error. Okay. Mean square error. Mean square error is okay. Fine. Mean square error is essentially your cost function, which I think many of you must be aware. Okay. So minimize the cost function, right? You want to minimize the cost function, which is essentially the sigma of your actual minus predicted value, the whole square. That is your mean square error. They also call the ordinary least squares. There are various terms which are used. So coming back to this multiple linear regression, now assuming that you have a data which has got profit, R&D, there are so many expenses. There's a venture capitalist who has this data from various companies, and he needs to take a decision as to which are the companies I need to invest. And he's looking at a machine learning model which will help him to predict or give him a picture as to which particular companies are the one where I need to invest, right? And one of the important parameters is, of course, the efficiency of the model, whether it represents, that model should represent the data. But secondly, how do I find using feature selection, or what is called the backward elimination method, how do I basically identify those features which is having a maximum contribution to my profit, right? Do is that for every feature, now this is something statistical, and and as I always tell my audience, whether it's my students or faculty, you have to have a very strong statistical knowledge, right? If you want to really pursue data science as a subject or as part of your career, right? So in the case of statistics, there is something called a p-value. Okay, so there is a p-value which is basically used in statistic, which is used to calculate how variability the data is. Okay, for example, you have a p-value of a feature. Now this p-value is calculated by using a function for every features. When I'm talking about every features, mean all the independent variables. And then you have something called a null hypothesis and an alternate hypothesis. Okay. Now what does this say? Now in statistics, there is something called a significant level. Okay. And that significant level decides what is your accuracy or what is the error rate, right? So typically we use a significant level of 5%. Okay, that means if your error is less than 5%, I'm good. If your error is more than 5%, I can ignore. Okay? That is how we use in statistics. So what does the null hypothesis say? My null hypothesis says that a feature has no impact on the profit. A feature has no impact on the profit. And the alternate hypothesis says that the feature has impact on the profit. On profit, right? And what this hypothesis says and what this statistical definition says that if my p-value of a feature is less than the significant level, that means significant 0.05. If my p-value of a feature is less than my significant level, that feature, okay, I can say alternate hypothesis is applicable. Okay, please ignore my spellings and all that. Let's focus on the content. So if my p-value is less than a significant level, then my alternate hypothesis is applicable. That means that particular feature has got a particular impact on my profit. Okay. Similarly, if my p-value is greater than the significant level, then my null hypothesis is applicable. Okay. So let's take an example. Assuming when I calculate the p-value for the first time, I get the values. There are three features, for example. I get values of 0.07, 0.08, and 0.04. Okay. And typically what I would do is, okay, now because this is less than 0.05, I will say this feature has the maximum impact on the profit. But this is not how we do. What we have to do, we take all the features, take maximum value of the p-value, for example here 0.08. Okay. So what I do is I take 0.08. So if this is my feature f1, f2, and f3, since f2 is the highest, I will, and it is more than 0.05, I will eliminate f2. Okay, I will eliminate f2. Then I take the remaining features f1, f3, and so on. I recalculate the p-value again for all of these, and again I find the highest one better than 0.05, and then I will eliminate again that variable. So you continue this till you get maybe the top two features, which will typically have, or maybe one feature which will have a value which is less than the significant level, and that is how I tell my client that this is the variable given highest impact, and based on that he can take a decision based on a combination of profit, and based on a combination of these variables he will decide where to invest. Right? So this is how we do what is called the backward elimination. Is there any questions on this? Have you guys understood? Can I get a quick yes or no on the chat screen? If you have understood, yes. If you have not understood, say no. Anybody has any questions on this backward elimination? Okay. So this is how it is so beautifully explained here.
Excuse me, sir.
Yeah.
Sir, when we compute the p-values for n different features,
yes,
will that p-value of one feature be affected by the other features?
See, the p-value is a calculation which is basically which tells when you say see when you calculate p-value, these are independent values you're calculating for various features. Okay, I will show you in the Python script how it is done, and then you show it with the significant level.
No, sir. If I have n features, and if I am computing the p-value for the first feature, second feature, etc., up to n features, if they are all independent from each other,
okay,
then even if I eliminate the nth feature because of higher p-value, and then if I recalculate for n-1 values, will they be different?
Yes, yes, it will be different. I'll show it to you.
Okay, that means everything they are not independent while calculating.
They are not independent, correct. But at the same time, you will see when I recalculate based on the features as I'm reducing, the p-value is not the same.
Okay.
P-value will change.
Okay, that means they are dependent, definitely dependent.
Correct.
Okay.
So p-value, there is something called the chi-square, which I'm
Okay.
not going into details. That is a way to calculate the p-value. I will show you a function which is used in Python where you calculate the p-value. I'll do that. Okay. And
this is exactly the same as the students' t-test.
Students t-test where you're talking about marks and all that, where we determine whether.
Yeah, I'm asking about the same thing, the significance test, you know.
Yeah, I mean, exactly. If you're talking of a multiple regression for formula where you're talking about multiple parameters which decides the output, yes, that's how we can use the p-value.
Okay, sir. Okay.
So I'm talking about multiple regression formula here, right?
Okay.
So what I will do here is I'm going to open one. This is a Python. This is Python Spider. What you see on the screen, and this Python Spider. I mean, I'm sure many of you may be aware that there are various interactive environments. You have Spider, you have Anaconda, you have Jupyter Notebook. Okay, you have Google Colabs. Various environments are there. If I install Anaconda Navigator, which is an open source, I get Spider as one of the platforms or one of the soft IDE platforms where I can write Python scripts. So this is where I write Python scripts, and this is where I execute through the console. This is where I get the output, what I execute from here. And this is where I have the data and all the variable explorer. This is the place where whatever I do as an output, I assign some output. Those outputs are basically stored here, right? So what I'm doing here in this case, I have my data set, which is 50 startup.csv, right? And this is the one I was talking about. So you have the R&D spend, administration spend, marketing spend, state and profit, right? So I'm not sure many of you whether you have done you are aware of data pre-processing, but I will just touch upon it when I actually run this. So in any model, when I execute, I'll have to do some sort of a data processing, right? Data pre-processing need to be done. Okay. I have to do some amount of data pre-processing. So what I have to first do is I will first, I mean, you must be all aware about the various libraries. So I'm just assuming that you guys are aware. So I'm just importing few of the libraries like the NumPy, the Matplotlib, the Pandas, which is used for importing data set. And I'm also importing the R2 score, which is used to measure the efficiency of your model. So suppose I execute this line. So I'm basically exporting my libraries. Then I'm reading my data set. So data set, when I'm read, I can basically go to my variable explorer and I can see what is my data set. So this is the R&D expenses, administration, marketing spends, state and profit, right? And then I identify which is my independent variable, which is my X, and Y, which is my dependent variable. And if I typically check it here, I'll value. So as I said, everything other than the profit will be your independent variable, and my profit is going to be my dependent variable because my profit depends on all these parameters.
Excuse me, sir. Excuse me, sir. As this execution is going on, could I get the data set as well as the code of this regression?
Yeah. I will send it to Anupriya ma'am.
Right. Okay. Thank you. Okay.
So what I've done here is that I have decided I know which are my independent variable. I know which is my dependent variable. Now, all of you must be aware about data categorization. I'm sure. Does anybody know what is data categorization? Does anybody understand what is data categorization? So what is the problem in this data set? In this data set, what is the problem? Do you see any problem with this data set?
Convert the categorical data, that is New York, California, Florida, etc., into numeric values.
Very good. So you need to convert all your text field to numeric because machine learning algorithms don't understand text. Okay, that is where you use data characterization, right? And in Python, there are two important libraries which are used. One is called the label encoder and one is called the one-hot encoder. So label encoder essentially creates. So if I just show you in the diagram, I have that with me, so that you guys get a feel. So this is my other. I'll just explain to you. It is, suppose I have got three countries, say India, US, and Italy, as my three countries in my data set. So what I do is that I first put it into a serial numbers. Say I make it 0, I make this 1, and I make this 2. Now, okay. And then what I do is I create an array of size 3 or dimension 3. Okay. And what does the array represent? The array represents the presence or the absence of that particular field. So if I got India, I will represent it as 1, 0, 0. And if it is US, I will probably represent it as 0, 1, 0. And if it is Italy, I will probably represent it as 0, 0, 1. Now, you really don't have to care how this is taken care. I'm just trying to explain you how data categorization works. And this process is taken care by a function called label encoder. Label encoder. Sorry, label encoder. And the process of converting this into array of variables is using one-hot encoder. Now, this one-hot encoder, what it does, it creates an array of these variables, and in machine learning language, this is called dummy variables. These are called dummy variables, right? So this is how you use label encoder and one-hot encoder function to convert any text field into a numeric format, right? And that's what I'm going to do here. Now, if you see here, I have got, these are the fields. Now, what I do is I run this function. And now if you see the value of X, now there were three countries here. So if you see your country was at the end, sorry, not the country field, the state field, right? Your state field was at the end. Now that state field was initial, what it does, it creates an array of three dummy variables, 0, 0, 1, 0, 1, 0. Okay. Now you don't have to worry how that mapping is done. That function does it automatically. But I just want to tell you this is how the three dummy variables get created. And then if you see the array of X, which was earlier 4 columns, now it has become 6 columns. Earlier that country text variable or the state variable got replaced by 3 dummy variables. So you have 3 plus those 3 expenses, right? So this is how you do data characterization. This is one of the very important data pre-processing steps, right? Now, what I also do in machine learning algorithms is now there is something called a dummy variable trap, because if there are too many dummy variables, it's going to make the processing more intensive, right? So if there are more number of countries, number of states, then the number of dummy variables tend to increase. So what we try to do is we try to eliminate, if you have got 5 dummy variables, if you have got 5 values, you can eliminate at least one dummy variable, because if you know the value of 4 values, then you know automatically what is going to be the 5th value. Okay, so you try to eliminate one dummy variable. So here what I'm doing is I'm just trying to eliminate one of the dummy variables. Okay, so my number of features has now become 5 instead of 6, right? Then obviously you are aware I will do split into a training set and test set. You are all aware of this. So you have a training set which is to train the model and a test set which is to measure the accuracy of the model. And typically we have a percentage of 70 to 30 in the industry. And here I'm using 80% training set and 28 test set. Okay. Now, one more important thing which I will talk to you later is something called feature scaling. I will come to that later when I come to PCA. Now, what I'm doing is I'm going to run my linear regression model on my training set, right? Okay, once my data, through the algorithm, once the machine or the model is trained, the model is now in a position to find out the pattern of the data. Everything in machine learning is all based on patterns. So you know the pattern of the data based on the correlation between the independent and the dependent variable. The machine will try to derive some sort of a pattern, right? And then what I do is I try to use my test data, use the variables of my test data and try to predict the output. I try to predict the profit. Okay. So, and then that predicted profit which comes from the model, I will measure and compare it with the actual profit of the test data. That is how you measure the efficiency of the model. So if I want to find out the R square of the model, it comes to 93%. Typically in the industry, if you have any model which has an accuracy 85% or more, we can always, it is something which can be recommended to the customer. Okay, any questions at this point of time? Is this clear to all of you? What I have done? Is it clear to all? Let me go back to chat and see if there's any questions. So you guys are clear, right? Very good. Fine. Now, let us do one more thing now. So as I said, I calculated the R square. Now I want to do what is called the backward elimination process. So I need to understand which features is having the highest impact on the profit. That is what I'm going to do. So what I'm going to do is I'm going to first, so I have got how many, so what I do is first I do this, what I essentially do here is I add something before, if I have calculation B0 plus B1 x1 have plus B2 x2, I also add something called B0 plus B1 x0 plus B1 x1. So I have an x0 which is typically, so my B0 is instead of B0 I give B0 x0 where x0 is typically 1. So I add one independent variable, right? So let this run. Okay, this is run. Now if I see the value of x, my x has got see the value of x. This for now. Bring this down. Okay. So my x is $50.06. So if I see the value of x, so I've basically added a variable called 1. Okay. Then I've got my dummy variables. Okay. So these are my variables 0, 1, 2, 3, 4, 5. Okay. These are my variables. Now what I will do is using this, I will calculate the p-value. There is a function called SMOLS, ordinary least square method, which is used for me to calculate the p-value. Now this is my p-value for the various variables. This is my constant x1, x2, x3, x4, x5. Now based on this, I find out which is the highest p-value, which is more than the significant level, right? So now I see here 0.99 is the highest, right? So what I do is I eliminate x2. So now I know that this is 0.99. I eliminate x2. So what I do now, I take the remaining 0, 1, 3, 4, 5. So I remove this one. So I have 0, 1, 3, 4, 5. And now I recalculate the p. Now, what is the p-value? Again, 0, 0.94, 0, 0.6, 0.11. See, the p-value is changing. As somebody had asked me, right? So see, the p-value is not same. The p-value is changing. And now see which is the highest p-value, and now 0.94. So I take out x1. So I have, this is 0. So now once I've run this, this is 0, 1, 3, 4, 5. And now I say 0. So I've eliminated this. I say now this one, this 0, 3, 4, 5. So constant x2, x3, x4. So now I have got 4 variables now. I've got to recalculate the p-value. Now I see again 0, this can ignore this. So this is 0.6 and this is 0.105. So which is the highest? 0.6. So again, I eliminate x2 and finally I have, again I do this and again I have, which is again 0.06, which is again the highest. So I will eliminate 0.06. So the one variable which is having the maximum impact is x1, which is the R&D expense. This is how I calculate. Obviously, you can write a function in a loop to do that. The reason of writing this separately is you understand how I eliminating one variable at a time to get a variable which has got the lowest p-value, which signifies that this is having the highest impact on the dependent variable. And this feature is called backward elimination. Any questions on this? Have you guys understood this concept? Is this clear to all of you? Can I get a quick yes or no on the chat box? Okay, so understand. Okay, great. Fine. So this completes about feature extraction. Now, the next thing which I'm going to cover, which is very important in terms of classification model, is wrong one, this one, right? The next thing which I'm going to talk to you about is dimension reduction. Okay. Can somebody tell me what is a covariance? Does anybody know what is covariance in statistics? What is the chat box? Let me now make this into slide mode. Yeah, anybody knows what is a covariance? What is the significance of covariance? So Dr. Rajiv Kaushik, what do you want me to explain?
Sir, this covariance, if you slightly explain.
No, I will explain, obviously. I just want, I will explain whether you have some idea about what is covariance. Obviously, I'm here to explain to you, but I just want to know if somebody has some idea about covariance.
Right, sir. Right, sir. Thank you, sir.
So essentially, what is covariance? It helps to determine the dependency of one variable on the other. Okay. So, and this becomes very important in a model because there are so many independent variables, and we need to know what is the dependency of one variable on the other. Are they increasing together, or means if one increases, the other is increasing, or it is negatively distributed? That means if one increases, other decreases, or that could be a scenario where there could not be any dependency. They are not at all they are independent of each other, right? There are a lot of various algorithms. There are various libraries available in Python. There is something called a Seaborn library. I don't know if you guys have heard called Seaborn, Seaborn, which is used to capture, there is something called a heat map. And that heat map, HEAT-MAP, which helps you to find the correlation between the various independent variables with each other. So very, very strong method, and that's where it uses covariance. Okay. And what is covariance is What is the covariance is, if there are two variables, whether it's one dependent variables, or even two independent variables, that's fine. Even to have a covariance, which is xi minus the x mean into yi minus y mean divided by n minus 1. That's the formula, where n is the sample size, right? So covariance, as I said, gives a set of direction. If the covariance is greater than 0, that means the two variables move together. If the covariance is less than 0, the two variables move in opposite direction. And if the covariance is equal to 0, the two variables are in row. The closer it is to 0, the less the dependency between the variables. That's what is called the covariance. There's also something called correlation matrix, where you use covariance divided by the standard deviation. Covariance divided by the standard deviation, that is something also called the correlation matrix, right? Now what is, and why I brought out this question is that today, as I told you, when I come to a classification data, for example, and I've got multiple features, and each features has got lot of variability in the data. So using principal component analysis, what we are trying to do is we are trying to reduce the number of features and come out with two new features. It will come out with, say, 2 or 3 new features which has a maximum representation of the data. That is all about principal component analysis. So what it is saying here, in principal component analysis, we detect the correlation between the variables using the covariance, reduce the dimensions of a d-dimensional data set. So if you have got 10 features, you reduce a k-dimensional data set, which typically we use today is 2. And as I told you, what is the advantage to have less number of features, because your model becomes less complex, and more important, your precision boundary becomes more accurate, right? Or the prediction boundary, not precision, the prediction boundary. So you try to come out with k features which is less than your initial number of features. So what PCA says, that from the n independent variables of your data set, you extract p less than equal to m dependent variables that explain most of the variance of the data set. That's a very important sentence. Extract p less than equal to m new independent variables that explain the most variance in the data set. Okay? And since for this variance which is computed, we are not considering the dependent variable, PCA comes under a category called the unsupervised model. It comes under the category called unsupervised model. So how do you go about doing the PCA? So suppose you have a lots of data. You have got data which has got multiple features. Okay, you got multiple features, and imagine that you have a classification data where your output could be a labeled discrete value or a categorical value. Okay, and you want to find out which are the variables. How do you find out using PCA? How do you find out the variables which are having, which will contribute the highest variance of the data, or which will represent the maximum information in the data, right? So the first step, what you do is you standardize the data, and this standardization is, why is it required? Because you have multiple variation in the data, and to bring that data, to standardize the data is basically you try to bring it to a level so that it can be easily compared, and that is where you use concept of feature scaling. Does anybody know what is feature scaling? Does anybody know what is feature scaling? Anybody? Okay, so let me explain. Imagine that I've got two data. Say, very simple example. I am the HR of a This is all we do on a daily basis, age and salary. Simple example. So I'm working in an organization. And obviously the HR age is captured my age. Yes, he knows my. Obviously, they know the salary of the total cost to the company, CTC, or the salary, right? Typically, my age will be from 21 to 60, right? And my salary could be from 10,000 to right up to maybe 10 crores or maybe more. I'm just giving an example. Maybe the CEO of the company earns 10 crores a month or 10 crores a year, whatever. Now, in machine learning, if you were to do a sort of a comparison between these two variables, it would not be possible as is, because these two variables are in different scales. So one is between 21 to 60, and other could be 10,000 to 20 crores. Now, if such a situation is come where you have a data, there is so much variability is there. That's where you use the standardization technique called feature scaling. So what happens in feature scaling is that you try to bring the values to a common base scale. And to do this, there are two important functions which do this. One is called the standard scaler, and the other is called min max scaler. And the function or the formula which is to do that is mentioned here. So when you're talking about standardization, it is essentially standard scalar function, and this is the function. This is how it calculates every min x divided by the standard deviation, which is root of the variance, right? And normalization is again x minus min x divided by x minus min x, and that is where you use the min max scalar function, right? And after you do this filtration, after you do this scaling, typically the values of your x becomes -1 and 1. Typically between -1 is 2 to +1 +2. That is how the values become. And this is very, very important when you are using PCA. So feature scaling is very, very important because wherever there is lot of variability in data, and typically in organizations, you will have lot of numeric data, and it is always advisable to, as one of the ways to optimize the model, you do feature scaling, right? So feature scaling is a very, very important thing. And this is an example how do you do a feature scaling using a standard scalar function. Okay, so what I've done here is, so I first standardize. So what happens is, if there are large differences between the ranges of initial variables, those variable larger values will dominate those with small ranges, right? Obviously. So what we do here using feature scaling, we try to bring it to a commonality, or we try to reduce the variability in the data. And that is when this function which you're seeing here, value minus mean divided by standard deviation, is what I talked to you about, the standard scalar. This is the standard scalar I talked to you about. Where is that one? Yeah, this is the standard scalar, x minus mean x divided by the standard deviation. So have you guys understood till this point what is feature scaling? Any questions on this point? The first step of PCA to standardize the data. Is this clear to all? Any questions? Can I get a quick yes or no? Okay, so you guys have understood. Very nice. The next step is what I'm going to do is to calculate the covariance. I calculate the covariance. So what I do is, as I told you, this covariance, if it is positive, means the two variables increase or decrease together. So if it is greater than 0, if it is negative, so they move in opposite directions. So if there are 3 variables, I calculate the covariance of x, xy, xz, yx, yy, yz, zx, zy. So this is sort of a vector. This is a vector or a matrix which I calculate based on the number of features. So if there are 7 features, I will have a vector. I'll have a vector with dimension 7 by 7. If I got 3 independent variables, I will have a vector of dimension 3 by 3. Okay. Now, what I do, so what covariance is saying, it is one of the statistical measurement to know the relationship of the variance between the variables. Okay. The covariance indicates how 2 variables are related and how help whether 2 variables vary together or change together. This I've already explained. And this is an example of how you calculate covariance. So this is the formula which I told you. And imagine that if this is your data, I'm just giving one example measure for people to understand. If this is my 2 data sets, if there's an economic growth and my S&P 500 returns, and I want to know how these are related to each other, right? So if I do the covariance, if you see it is 0.533, which means these are very, very strongly related in the positive directions. So if my economic growth increases, my S&P returns also increases. Okay. So if my economic growth increases, and this is how I calculate my covariance, right? What is important here is a concept called eigenvalues and eigenvector, and this is again a very statistical thing. I'll give you some links how to calculate the eigenvalues and eigenvector, right? It's a more detailed, which is cannot be covered here. I will give you some links in this PPT, but which you can go through, and lovely explanation is given. So what it's doing is there. Imagine that if you have got 3 independent variables or 3 features, okay, if 3 independent variables or 3 features, there'll be 3 eigenvectors and 3 eigenvalues. If there are 5 features, there'll be 5 eigenvectors and 5 values. Okay. So what I do is I obtain the eigenvectors and eigenvalues from the covariance matrix. So once I have the covariance between the various features, based on the statistical calculation that I do, I can obtain the eigenvector and the eigenvalues. I sort the eigenvalues in descending order. Means I have the eigenvalues the highest on the top and the lowest at the bottom. Okay. So when I say the eigenvalues which are at the top, those represent the highest variability in the data. Those represent the highest variability in data. So sort eigenvalues in descending order and choose the k eigenvectors that correspond to the k largest eigenvalues, where k is another dimensions. So if you have 10 dimensions, you will 10 features, you will have 10 eigenvalues. You sort it from descending top to bottom, and then the top 2 or 3, as you see, the top eigenvectors or the eigenvalues will represent the highest variability of the data, or that will represent the maximum information in the data. Okay, so instead of having 10 features, you can bring it down to 2 features, which is going to be which is contributing maximum to the data, and that is where you use the concept of a feature extraction. Okay, so this is an example where you have the various vectors and you calculate. This is the eigenvector, and this is you calculate the eigenvalue. And as I said, as you basically you sort it by the eigen values, the one which is the top level. So you take, there are what is called the principal component. Principal component is you take the highest value, which is giving the highest, which is representing the most variety data. So you have principal component 1, and the second is principal component 2. Okay, so the principal component 1, which is giving the highest variance or the highest eigenvalue, and this principal component 2 is something which is giving the next level of eigenvalue, because you have already done a descending order of eigenvalues, right? And these are the various links which I have given you. You can go through. There's something called pathmind.com. There is something called statistics. there's a YouTube wonderful thing where you can how you calculate the principal components, and there is something Sebastian RACHK various articles which I'll share this PPT with you all. So please go through this and you'll be able to understand about the vector and
I'm uploading it in the Atal portal, as well as I will upload it for the
yes, ma'am. Yes, ma'am.
participants.
So after this session, I will send it to you only. Don't worry.
Yes, sir.
Okay. So once you have this, once you have the components which contributes the maximum variability of the data, okay, and then you find using these two new variables which created, these principal components are the two new variables, you find out the accuracy of the model. And that is what I'm going to show you in my next example. So what is the principal component? Principal components are new variables that are constructed as a linear combination or mixtures of the initial variables. They represent the directions of the data that explain the maximum amount of variance, the lines that capture most information of the data. The amount of variance, the lines that capture the most information of the data. That is how basically you are finding out two new independent variables that using PCA. And if I draw a graph versus how the variances are explained based on the number of features, this is how I have sorted it. So the top two, maybe this is 40%, this is 20. So this two gives you the highest representation of the variance. As the number of features goes up, the data, I mean, these don't explain much of the variance, right? So always ignore the ones are having or giving a lower representation of the variance. Okay, so you can always ignore this and only take top 2 or 3. This is how you calculate principal component, and mainly we in the industry we use principal component 1 and principal component 2. Okay, any questions on this PCA before I show it to you in Python? Anybody has any questions on PCA?
Sir, actually session time ends. So can we continue the session by 3:15, sir?
Okay, we'll do that, ma'am.
Yeah.
Please come back by
So,
3:15, okay?
No, you can start, sir. We can start sharply by 3:15 because since we were few minutes late, I'm breaking up by 3:05. We started around 2:05 only. That's the reason we are
No
starting.
problem. I will. Don't worry. I'll go beyond. Don't worry. I'll my everything what was required.
Using it by 3:05. Turn by 3:15. Do not disconnect. Stay tuned and get back by 3:15. So we can continue the session from 3:15 to whatever time, like till 4 o'clock or even after 10 minutes or something.
Yes,
even
yes.
after that,
No.
we will complete the session. Yeah. Thank you, participants. Go and stay tuned with us. Good afternoon, participants. I hope you're all back.
Is my screen visible?
Yes, sir. Your screen is visible.
Okay.
So we just completed the feature extraction process, and I think, sir, how many slides are pending? 1 or 2 slides?
I want to show one demo on PCA. Then I will go to classification ANN. So another 5 minutes on the demo, and then I'll go to ANN.
Sure, sir. Sure. So participants, so there will be a small demo on the principal component analysis. Followed by that, classification techniques will be discussed by Arunjit sir. So, sir, I hand over the session to you. Please proceed, sir.
Right. Okay, so welcome back, guys. And so now I'm going to actually show you about PCA. Where is that? Okay, so I'm now going to show you PCA actual running. Okay, now what I will do is, this is my file. My file name is pca.py. Now, what is the data set? Now, this data set, okay, let me first put it and then I can show it to you in the under Variable Explorer. So I will import my libraries. I will import my data set. Okay, and let me go to Variable Explorer and open the data set. Okay, so now this is my data set. Now this is basically there are various constituents which get into in the wine industry, right? And based on that, these constituents decide which customer segment of people is going for this proportion of these features, which customer or segment is going. So you have each customer segment, which is typically 1, 2, and 3. There are 3. Okay. So depending on the constituent of the features which makes up the wine, you have a customer segment, which is 1, 2, and 3. This is a classification data because your customer segment is your dependent variable, and it has got fixed values 1, 2, 3. 1, 2, 3. Okay. Now, what I am going to do now is that, so everything, so my independent variable is all the columns except the classification segment, right? And the customer segment is Y. So if I see X here, X is all my values other than the classification segment, and Y will be 1, 2, and 3, which is the customer segment. Correct? Now imagine 13 features. How many features are there? 13 features. So 13 columns, and one column obviously for the, there will be always one dependent variable. There could be as many number of independent variables. So we are having 13 variables, 13 features of X, which is your independent variables. Now what I'm doing, I'm a split into X train and X test. So 80% is my total number of records is 178. So I will break it down, okay, into 36 and 142. So 142, 36 is 20% of 178, and 142 is 80%. So if I see my X train and X test, if you see my X train, this is my X train and X test. Okay, so these are my data for X train and X test. So this X train has got 30 independent variables. X test has got 13 independent variables. Now what I will do is I will use my standard scaler. This is the standardization of function which I told you. This is the first step you have to do. You have to standardize the data because there could be a lot of variability in your data. So I standardize my data using the standard scaler. Now see, that is how it will look after I do this standard scaler, which I'm going to apply on X train and X test. See the value that comes up. Okay, very interesting. See X train. The value is coming to 0.87, 0.79, 0.64, minus 1.06, minus 0.205, right? These are the various, this is the outcome of the standard scalar function which is used. So the value is typically between -2 and +2, typically, right? Similarly,
Excuse me, sir.
Yeah, please go ahead.
Excuse me, sir. I'm sorry to disturb.
Sure,
But
no
is it mandatory to apply the standard scalar on X test also?
Yes. You have to do it for X train as well as for X test.
Okay.
Yeah. So now that you have done the feature scaling, you have standardized the data set. Okay. That's what I'm doing here. I'm saying that I'm going to have two principal components. I'm saying I'm going to do this on X trace and X test. I'm going to use something called the NCA function, and this will reduce the number of variables of X train and X test. See, now there were 13 features. Now when I run this, okay, when I run this, my X train is now, if I see X train here, sorry, this I've already done, my mistake. I'm only here now. I'm going to use this, okay? Okay, now you see, if I see X train, X underscore train, now there are two features. So these two new variables are getting created, which explains the maximum variance in the data based on the eigenvalue, right? Similarly, if earlier it was 13 values, now there are two values. See, now see X train come 2. Can you see the number of variables, which was earlier 13? Now X train has become 2, X test has become 2. Okay. Similarly, if I see X test here, it will be again 2 variables, right? Now that I have got 2 variables, now I have got one dependent variable. So I have now 2 features, independent variable and one dependent variable, which is the customer segment. So I have captured the maximum variance in the data using the principal component analysis, and using that I have freezed down this to 2 new variables, 2 new independent variables. Now what I will do is, now I could use various classification models. I could use logistic regression, decision trees, random forest. Okay, I could use KNN, so on. But for now, I'm just using logistic regression to find the accuracy of the model. So I'm training the model, I'm predicting the output, and then I'm calculating the confusion matrix. So I'm not, guys, get into what is confusion matrix. I'm assuming you all know all that. So when I calculate the accuracy of the model, you will see that the accuracy is how much? There are total 14, 15, 30, 36, right? 36 test data. So 35 out of 36 is my accuracy, because there's only one data where I'm assuming that this is 1, 2, 3 predicted and this is 1, 2, 3 actuals. So in these 3 cases, the model is behaving fine. Only in this case, there is an error. That means the model is predicting something, but actually it is something, right? So this is where you, using PCA, you'll be able to get better accuracy about the data, okay, with less number of features, okay. And if I want to see this in a graphical mode, let me draw this. This is how it looks. So you have, this is for training data. So what you have, this is your PC2, principal component 2. This is your principal component 1. This is your prediction boundary I talked to you about. Prediction boundary, these lines. This prediction boundary demarcates the customer segment 1, customer segment 2, customer segment 3. And you see the green dots in green, that means we are good. The actual value and predicted value is fine. You see red values in red, we are good. You are seeing blue values in blue, it's okay. But you will see some red values in green boundary, and there are some green values in red boundary. These are all the errors. I don't know if you have heard what is called the type 1, type 2 errors, which you get in confusion matrix. These are the type 1, type 2 errors. This is for the training data. Now, if I want to run this on a test data and see how the model is behaving, see how it looks. You remember there was only one case out of 36 where there was an error. This is the one. So there was one case where my actual value was 2, but my predicted value is 1. Actual value was 2 for the customer segment, but the model predicted 1. That was the error. But barring that, all others were fine. So this model works pretty fine with using the PCA. So have you guys understood about this PCA analysis? What has been done in using scripts? Is this clear to all?
Sir, after application of PCA, the new 2 features are there. Okay, what is the name of those 2 features?
No, there is no name for those features. These are new variables that got created. Okay, which is a subset of x and y, x1, which is a subset of x.
Okay.
It's a new variable. It is not one of those 13 variables. They are new set of variables. So once you do that reading on the eigenvalue and eigen how it is calculated, you come to know. Okay, so these are called the principal component 1 and the principal component 2. That's what you see here, PC1 and PC. These are the 2 new variables.
Okay, thank you.
Okay, so this completes my feature extraction and feature elimination, basically my dimensionality reduction. Any questions before I get into ANN? Okay, if there are no questions, let me jump through ANN. Okay, now can somebody tell me? Yeah, please.
Sir, is there any limit using feature? How many number of features we need to input for PCA?
No, there's no limit. In PCA, generally recommended is 2. Less number of features is better. 2. 2 or maximum
Okay.
3 you should use. Yeah, yeah.
Okay, then it will work on only supervised learning.
Yes, yes. This will work only on supervised learning. Yes. This will work on classification. Yeah, this will work on classification. Okay.
Okay, sir. Thank you.
So now let us go back. Now let us get into ANN. Okay, I'm going to explain to you. I mean, many of you, can somebody tell me why ANN has become so important in artificial neural networks? Why is it become so popular? Or why is it required?
It works for back propagation. It like feature how many if the model is not working, we are going back and we are selecting the features like that. So back propagation works.
My question is different. Okay, before that, Subbalakshmi Das had a question: how to use feature for feature extraction in images. So, Subbalakshmi, there is something called image segmentation. There are various such mechanisms which are used for feature extraction, so which I'm not covering here. So, there is PCA can be used both in artificial neural networks as well as in convolutional neural networks, right? So, you have something called image segmentation, and there are some mechanisms where you can do image filtering and a lot of things by which you can calculate the or remove the unwanted or only pick up the important features. Okay, Subbalakshmi, does that answer your question? Okay, so my question is why ANN has become so important. Not why you're explaining what is ANN. I'm trying to understand why ANN has become so important. So essentially, what has happened is as the number of as the complexity of the data increases, okay, as the number of features increases, a normal machine model, if you try to execute, it has never found to be that accurate. Okay, and which as you increase number of parameters, number of features, the processing intensity also it becomes more processing intensive, right? And that's where when they come across neural networks, it's all about how do you, if you compare to a brain cell, so it's all about how do you basically use processing using mechanisms by which you can predict the output in a faster time. Okay, and neurons, if you why they're called neural networks, because it represents your neural brains. In your brains you have various neurons which is used to transmit information or data from one point to another, transmit information from one neuron to another. Okay, and that is where the concept of neurons came in ANN, artificial neural networks. And artificial neural networks is also used in CNN also. If you talk about CNN, where you do the image detection using the various steps, okay, and then ultimately you create one layer which is an input to the ANN. So ANN is all about how do you basically classify your input data. So you have a lot of input data. Imagine that you have got multiple features. Okay, let me make this in a bigger screen. You got multiple features and you have got something called layers, hidden layers in ANN. And after that, you have an output layer where you predict the output and then compare it with the actual. Okay, here again, you have the concept of error cost function. Your main object is you have to ensure that your output predicted value and the output actual value are the same, are close to each other. Okay. So typically, if I see you have the neurons out here, you have the neurons transmitting information to another set of neurons through this is called the axon. These are the dendrites, which are the inputs. These are the inputs to the neurons, and these dendrites or the inputs are your input variables. Suppose I have got multiple features like M1, X1, M2, X2, M3, X3. Then this X1, X2, X3 becomes my input variables to my, these are to my hidden layers, to my neurons in my hidden layers. Okay. Now, typically there are two types. One is a perceptron, where you have just a single neuron and it gives a binary classifier, which gives a yes or no, for example, or 0 and 1. And there is something called an interconnected multilayer, where various inputs, there are weights adjusted, there are weights assigned to each of these values. We'll come to details what is weights. And all these, this is input layer, this is various, this hidden layer 1, hidden layer 2, this, and this is the output layer. So all these are interconnected. So this neuron will activate this neuron will activate this neuron will activate this, and so on. And finally, you get an output. Okay. So what is very important in ANN is something called an activation function. And this activation function becomes very important and in the hidden layer as well as in the output layer. There are various activation functions used, and why these activation functions are used is to bring about some non-linearity in the model. Okay. For example, if I got x1, x2, x3 as my input independent variables, and these are the weights which I'm assigning. Okay, I do a summation of wi xi, which is a one step, and I using an activation function, I come out with an output value, and that output value also will determine whether it is close to the actual or it is far away from the actual. Okay, so you have an activation function from the, now these activation functions is used in the hidden layers as well as in the output layers, and which activation you have to use where, I will explain to you. Okay. So what is the advantage of activation functions? So activation functions is basically used to introduce non-linear properties in the neural network. They convert the linear input signals into non-linear output signals to facilitate the learning of high order polynomials. So wherever you have got high normal complex data where you have got x1, x2 square, x3, multiple polynomials which goes to one or multiple degrees in networks, it is very important that you need to do activation, and without, if you don't do activation, the model will not work as desired. Okay, and you have to use activation functions whether you are using regression, classification, or whether you're using images, speech, audios, you have to do activation functions for various types of data. Okay, there are various algorithms, there are various activation functions used for even NLPs, natural language processing. I'll come to that. Okay, so this activation function is very, very important in ANN, and it is applicable both in the hidden layers as well as the output layer. So one of the important activation functions which is used in the output layer is called the softmax or the threshold. And what it does is that it is typically in a binary probability or a multi-class probability. When you say binary probability means the value could be either 0% or 100%, right? And multi-class probability is the probability of an output could be total 100%. Maybe if there are 3 outputs, I will say it will be 30% probability of 1, 30% of 2, and 40% of 3. So there is a multi-class value. You could have 3 values, and the probability of each value could be 30%, 40%, 50%. So total becomes 100%. So that becomes a multi-class probability, right? So in a case of output layer in classification, where the value will be either 0 in a multi or binary class probability, we typically use what is called the threshold functions, and here typically the y will differ between 0 and 1. This is after applying the activation function. Okay. Then you have the sigmoid. Sigmoid is also used in output layer, but again, in this case, it is mainly used for binary class probability. That means where the output values is 0 and 1, use sigmoid. But if you have a multi-class probability, then you use the threshold or the softmax. Okay, that is the activation function you use for the multi-class probability, right? In the hidden layers, the most prominent function, activation function we use is called the rectified linear unit, ReLU, right? And typically, if you see here, the values will be maximum of x. X is what? Sigma of wi(xi) or 0. Okay, that is how it brings down the value to either the maximum of the sigma wi(xi) or 0, whichever is the higher. Okay, that is how it will restrict the value to a specific particular value depending on the activation function. So this activation function ReLU is used in the hidden layer. Okay. Then hyperbolic tangent. This is again used in recurrent neural networks for NLPs, speech recognition. We use hyperbolic tangent activation function. It's a very complex function, and the output typically varies between -1 to 1. That is how you use for. It is typically used in RNN or it is used for NLPs. Okay. Linear activation RNNs, you use it if you are using linear regression function. So if you have a multiple linear regression function, so for activating, okay, you use the linear activation function, right? If you sum it up, so you have the input layers, you have the weights, you have the activation functions, you have the activation function at the hidden layer, which you can typically use. This I'm using if this is a single neuron and an output, then you are having either the activation function or the sigmoid activation function. Okay, because if the binary is 0 or 1, so depending on whether you have a multi-class probability or a multi-class, or either 0 and 1 binary class, then you decide whether you go for a sigmoid or you go for the threshold function, right? So this is again explanation of how we are using rectifier here and sigmoid here. This is how it is represented in a typical neural network function.
Excuse me, sir.
Hello, yes, sir. Yes.
Sir, actually, in case of ReLU, sir, if I have the positive and negative, if I have positive values, negative values, or a mixture of both positive and negative, so how the ReLU activation function will work out?
So ReLU will be taken. That's what I'm saying. It will do a sigma of wi(xi). Okay, the weight into the value of that x values, right? And then it will, the activation function, it will take maximum of like sigma xi or 0. It could be than 0. So if it is less than 0, it will be 0, or it will be the value of sigma wx.
So the negative values will be replaced by 0, and the
Correct.
rest values will be as it is. Okay,
Actual value. Correct.
Thank you, sir.
Okay. So assuming that you are talking about a multiple regression function where you have the price of a house, and the price of the house depends on various features. It could be the square feet, it could be the feet, the number of bedrooms, the distance to the city, the age of the house, or how new is the house. All these parameters may decide the price of a house. So this becomes a multiple regression. So if you use a multiple regression and use the ANN technique, then these are all your input. This is again your neurons in the hidden layer, and this is your output, which is your price. So you use the linear regression activation function in this case, right? Similarly, when you're talking of soft-patch activation, where if you're having a multi probability where the output could be, there are 3 values which could be 67%, 24%, 9%, where the weight, texture, color, and size will decide the probability of a particular class having 3 values, could be 67, 24, and this is multi-output software activation function. Max. What is gradient descent? Okay. Now, typically what happens is that in ANN, you have something called a weight, right? This weight is, this initially some weight value is assigned, okay, to x1, x2, x3. So you have w1 for x1, w2 for x2, and so on. You assign some x value or a score to the weights, okay. Then you calculate the sigma wixi. Then you do the activation functions and come out with an output. Now, when you come out with an output, if the output doesn't match with the actual output, that is where the cost function. What is the cost function? If I want to minimize my cost function, or if I want to minimize the mean square error, the sigma of yi, that is my actual yi minus y predict of predicted value, the whole square, okay, should be close to 0. Okay, that means I have to minimize my cost function. So what happens is that whenever I apply a weight to a particular x1, x2, I put some scores, I do a sigma wixi, I do an activation function, and then I predict the value of the output. And then output is a classification. If there is an error because my output and this is not matching, that means my cost function is very high. Then what happens? There is something called a learning rate. So that learning rate is adjusted every day based on the error it has encountered. And based on the learning rate, weights are again adjusted. And the weights are adjusted in such a way that your sigma wix, you work in such a way that you adjust the learning again, the learning, what do you call the learning rate. Based on that, you adjust the weights in such a way that you eliminate the cost function. And this is basically what is called the forward and backward propagation. So when you have the inputs here, you give the weights a score. Okay, you do the activation function, okay, the output. If there is an and again you basically it will update the weights and try to minimize the cost function. So the forward propagation is the first time, and the backward propagation is adjustment of the weights to see how we can reduce the cost function. And this is how and ANN works. It's all about forward and backward propagation. Okay. And this delta E is the bias. This is the learning rate. Okay. And B is the bias.
Excuse me, sir. Excuse me, sir.
Yeah. Yeah.
Can you please move back to the yes. Here there was a network break at your end, perhaps. Can you please repeat a little bit?
So,
thank you.
So these are the inputs you are aware. So we are talking of x1, x2, x3. Okay, these are the inputs. Okay, and this is various neurons, right? Now initially you give some code to the weights W1, W2, W3. You apply the activation functions ReLU here. You apply the activation functions sigma, say a sigmoid or threshold, whatever. You get an output. And suppose the output is a binary class, either 0 and 1, right? Now, once it is 0 and 1, and suppose the value doesn't come to 0 and 1, it is something which there's an error. What I will do is, I will adjust the learning rate. So there's a learning rate, which is as part of the gradient descent. It will adjust the learning rate, and based on the learning rate, the weights are recalculated. The weights are recalculated, and again there's a backward propagation till we get a final output again, which is close to, I mean, the output value, predicted value is close to the actual value. That means you want to reduce the cost function. Okay, this is basically the forward propagation, and this is the backward propagation. Okay, so as I said, this is the formula for cost functions. Half yi, this is y predict. That is the predicted value coming out of the model, and the y actual, the whole. So this is the cost function, and you want to minimize the cost function. That is what you want, right? Now, there are two types I want to explain. One is called the batch gradient descent, and one is called the stochastic gradient descent. What is a batch gradient descent? In a batch gradient descent, suppose you have a data of 10 records, you will, what I will do is, I will take all the data together. I will do a forward propagation. I will then update the weights at the end. After reading all the records, I will do the update of the weights at the end, and then I will recalculate the cost function. If I look at stochastic gradient descent, what happens is that I take a batch size of data. Suppose there are 100 records, I take a batch size of 10. So I take the first 10, I take the 10 records, do a forward propagation. Then I update the weights after the 10 records based on the learning rate. I will again do a backward propagation. Again take the next set of records. Again do a forward propagation, backward propagation. Take another 10 set of records, forward propagation, backward propagation, until I complete all my 100 records. And once I complete the first set, one cycle of 100 records, which is my total data set, I say I have completed one epoch, which is called EPOCH, epoch. And then I again, at the end of one epoch, again based on the condition, based on the the accuracy function, I recalculate or I recalibrate the weights. Based on the learning rate, the learning rate is modified, the weights are adjusted again, and again I run another set of epochs. Then again I run third sort of epoch. So the idea that after each epoch, my objective is how I can improve my accuracy. So typically industry, when you're going to implement NN, you have to know how much epochs you have. So typically, and what is the batch size? Okay, typically you will see that people use epochs 100, 550, 100, 150 also. So it's a trial and error. Initially, when you're new to a project, you will try with various epochs and see how much accuracy you get. Okay, and then as you gain experience, you will know that what is the optimum number of epochs you can use to get the highest accuracy or the lowest cost function. And the stochastic gradient descent is very, very prominent today. And that is what is used to the industry, the stochastic gradient descent. And that's where you are seeing here, it adjusts update there after each training sample or batches. Weights are adjusted in every iteration as to and the cost functions. After each batch, the weights are adjusted due to the backward flow. That's how it works. So any questions at this point? Have you understood what I'm trying to say here? Forward propagation and backward propagation. Have you guys understood? Is this clear? Can I get a yes or no on the screen? Okay, so you guys have understood what is batch propagation, sorry, what is forward propagation, what is backward propagation, what is gradient, what is stochastic gradient descent, and what is epoch descent, right? This is a lovely slide which will give you the complete pictures beautifully. First, it says randomly initialize the weights to small numbers. Okay, that's how it works. Input the first observation of a data set in the input layer. Each feature is one input node. Okay, so we have so many nodes, so one input. From left to right, the neurons are activated in a way that the impact of neurons activation is limited by the weights. Propagate the activation until getting the predicted value y. That is y predict. Compare the predicted result to the actual result and measure the error. So you will know what is the cost function, right? From right to left, the error is back propagated. Update the weights according to how much they are responsible for the error. The learning rate decides by how much we should update the weight. Okay. Repeat steps 1 to 5 either after each observation, which is used in reinforcement learning, or you also call it gradient descent, or you can do it after a batch of observation called a batch learning. So you can do it after batches. So as I said, you have batches of 10 out of 100 records, you do for 10 batches, that is complete one epoch, right? That is how you do 10 times, because there is a batch of 10 and there are total 100 records, right? So an epoch is a complete pass through a complete data set, while an iteration is a forward and backward propagation for a single set of data is an iteration. But when you have a batch of data and you taking the total batch of data and then you're doing the forward and backward propagation for that set of data and adjusting the weights, that's called an iteration. And multiple iterations will make up a epoch. That is, really completes the entire data set. So one epoch is a complete data set of 100 records. Okay. So this is again the same thing. These are all examples. This is some of the data preprocessing. I just kept this because I wanted to explain all the data hot labeling order, one hot encoder. So I kept this slide so that you guys can see it later. How you split the data, feature scaling. So all these slides are there, which I've kept for you. Now what I'm going to do is I'm going to show you it on the screen in Python. So I'm going back to Python. What I will do, what is this question? I didn't understand, Dr. Harjit Singh. Fine. So what I'm going to do, I'm going to, let me just initialize the kernel here. When I initialize the kernel, restart the kernel, I'm just going to initialize all the variables here. So it is all blanked out. Okay. I will just close this. And I will select a data set. Okay. Now this is my data set, ann.py. Sorry, this is my script. And my data set is, let me first import my data libraries. I import my data set. And let me view it in the variable explorer. So there are 10,000 records and 14 columns. Now what this data set is all about? It says this is a bank. A bank is capturing the information about all the customers. His credit score, his demography, how much is his savings balance, and we want to basically find out the probability of a person, the churning of a person, basically in a bank, okay, whether a person is going to leave the bank or not, right? So to do that, so there is a data which I have created that based on the various profiles of a person, I know my output whether it's going to exit or not going to exit, whether it's going to exit the bank or not, to go to some other bank or not going to exit. I need to study the behavior of the customer using a machine learning model so that I can basically come out with some of that campaigns or some innovation so that because as a banker, my objective is to retain the customer, right? So how do you come out with a model which will be able to predict first of all the data, and then depending on the type of data, I can decide, okay, what sort of action I need to take for that particular customer. Okay, so in this case, what I'm going to do, I'm going to use the ANN model. I'm going to use ANN. Okay, now what I will do, first I will decide which is my independent variable. So which is my independent variable? All the values except for the churning yes or no, 0 or 1. And my Y is the last column, which is my independent variable. Sorry, dependent variable. So 0 and 1. Okay. Now what I'll have to do is from this data set, you all know. Okay. Now from this data set, what I'll have to do is that which are the fields I need to convert into text, which are text. One is my country and one is my female. Now, please understand here that when I took X from here, I don't care about the ID. I don't care about the surname. That is the thing for me. I need to understand what are the other parameters which help me to determine whether the customer is really exiting my bank. So if you see my from column 4, is 1, 2, 3, 4, and it's 4. If I see X here, is basically starting from, if I see X, my X actually starting from 19, this is my 24, and then you have the 3 and the sex. Now I've got country and sex, the text is, I convert that by data into a format using label encoder encoder, which I already explained you before the break, correct? So what I do, I do the label encoder for both the variables. I reduce one of the dummy variables. As I said, I can reduce one of the dummy variables. Now if I see X, 12 and Y is and 10,000 records. What then? I split my data into any set as. So do this. So my strain is 8,000 records because 3%, and X is 2,000 records. So we are clear on this, right? Similarly, we have a white test where white train is again 8,000 records and white is 2,000 records. Okay. After that, what I do, I do the feature scaling. Okay. Again, the feature scaling because there are too many features and I don't know the variability of the data. Okay, so I will do a feature scaling because all the data could be different scales. So I will do a feature scaling on X-ray and X-ray. Now see X-ray here. This is what I see. Okay. Now if I do feature and if I now X-ray, this is how 0.7 minus 1.7, 0.64 and so on. So I can give values for the different records. This is the standard scalar function. Okay. Once I've done the feature scaling, that is where I am now completed all my data pre-processing and I'm good to train the
Sir, can you hear me? Sir, your screen as well as voice is not audible. Screen is also not seen, sir. Arun, sir.
Am I audible now?
Yes, sir.
Okay. And let me know once you're able to see my screen. Are you able to see my screen? Is my screen visible to all? Okay, great. So what I have done now, I have imported my keras. I imported a class called sequential. From this library, I imported sequential and dense, which are libraries. Okay, then I use this function to initialize the ANN. Now what I'm doing here is I'm creating the middle layers, hidden layer. So in the hidden layer, what I'm saying, I'm using 6 neurons. Kernel initialization is uniform, activation is ReLU, that is the activation function which I'm going to use for my hidden layer, and input dimension 12, because there are 12 variables in my independent variable. I'm going to take input dimension 12, and so I will create one hidden layer. This is how my hidden layer will get calculated. Okay, I'm saying that I will create another hidden layer. So I'm saying again another 6 neurons. I'm saying activation ReLU. Now the question is that how many times hidden layers you're going to, how many hidden layers you're going to create. Now that will again depend through experience. So initially we start with 2 or 3 hidden layers. You can increase and see whether there is an increase in accuracy, or with the same number of hidden layers you increase the epochs and see whether you can increase the accuracy. So you have to try various combinations of changing the epochs or changing the hidden layers to get the lowest cost function or the highest accuracy. Okay. So now I created second hidden layer and I created one output layer. In the output layer, I'm using activation equal to sigmoid. Okay, sigmoid because I've got binary classification 0 and 1, so I can use sigmoid. Okay. Now what I do here, I'm doing, so I'm going to use something called matrix accuracy. That is for classification model. I use a matrix accuracy, and loss should be so loss has to be minimum, right? So I use, because I'm using stochastic gradient. Adam means I'm using stochastic gradient, and loss binary cross entropy. This is one parameter used. Okay, because we are having binary values of the output, and matrix equal to accuracy, which is my accuracy for a classification model or a confusion matrix. So I run this is the parameter I set, and now what I'm doing, I'm taking X train, Y train, I'm taking the training set, I'm taking a batch size of 10 and running 100 epochs. Means if there are 100 records, I will run with a batch size of 10, update the weights after the one batch size, adjust the learning rate, another 10, 10, 10, up to 10 times 100. After that, one epoch. Again, another epoch with a revised weights and learning rate. Again, second set of epoch. Again, third, fourth, fifth, sixth, like up to 100. And that's what this will do. Let me run this now. As you run this, if you see, it is taking a batch size of 10. Okay. And since there are 8,000 records, so there will be 800 times it will run per epoch. Okay. And you will see the accuracy. The loss has to come down and the accuracy has to go up. Okay. Okay, so now it has got an accuracy around 84%, which is still, I will not say it's a very optimum. I would have got at least, I would have expected 85%, right? Okay, so maybe what I will try, I will try more hidden layers. Or another try I can do is I can increase the number of epochs. Okay, so I can try with various options and see where I can get the maximum accuracy, right? So now, having done this, now I'm going to use, I can, with my model trained, I'm going to predict the output with my test data. And using confusion matrix, I will compare the predicted value and the actual value, and my accuracy is coming to 84%, which is nearly 84 here, right? 0.83, 0.8 is 84%. So this is the way I calculate the accuracy of a classification model using ANN. Okay, is this clear to all? Have you guys understood what I have done in this particular steps? Is this clear to all? Can I get a quick yes or no?
Sir, please explain units is equal to 6 parameter.
Hello, sir. Are you able to hear him or see his screen? Can anyone respond on the, respond in the chat? Hello. Can anyone please respond in the chat? Okay, okay. Participants, sir has informed that he has got the connectivity issue, but he has reached towards the end of the presentation. So, sir, he said by the end of the day, he will mail me the presentation as well as the so I can share with you. So this is to kindly remind you to give the feedback which I have already circulated. And as per the discussion we had, 7 o'clock I will post the assessment. 7 to 7:30 you try to complete the let me know, otherwise we can close down. So tomorrow will be day 3 and we will be focusing on the deep learning techniques and deep learning techniques, different techniques and the optimization techniques. From Trivandrum, Sri Chitra Tirunal College of Engineering, and Dr. K. Ganesan, Senior Professor from VIT University, will be presenting the sessions. So this is just an overview of previous sessions. Thank you all for your patient listening. We will what is that? We will start the session tomorrow by 9:30. Yes, please.
Feedback link is not working now.
Madam, there is a voice break. Can you please put your request in the chat box? Can you please put your request in the chat box, because there is a voice break. Even I am after 4 o'clock. We also, like they are closing. So box, I will reply to you. Feedback.